Okay, and we'll start from, now don't tell, yeah, there it is. Okay, I was going to say they've already lost that. So we'll go from current slide, and that's where we begin. So again, I'm sort of surprised we only got 4 students here. This is amazingly low. I'm glad y'all are here, but I don't know where the rest of the folks are. Now, there's several things I want to bring up now. I think I brought some of these up before, and if you aren't familiar with them or not too, if this seems like new word to you, be sure to ask questions. Okay. Right now there's a faculty meeting going on. I had to get out of it to come to class. This now is my 1, 2, 3, 4, 5. This is my 6th Zoom meeting today. Okay. This morning, and this goes to a lot of things that we're going to be doing today. This morning, or let me start with last evening, I was putting together the lab for today. Okay, I didn't get to type it in, but I was organizing it and planning what we were going to do, and looking over the things and figuring out how to do it. But I just ran out of steam, ran out of gas, ran out of energy last night, so I quit sometime 9:15, 9:30, and thought, well, I've got a half hour in the morning, I'll try to finish it then. And then I've got 2 hours in the day that I'll finish it then. Okay. Well, this morning, about my first class was 8:30. About 8:23, 8:24, I usually stop whatever I'm doing and give myself 5 minutes to get the class set up. Well, about 6 or 7 minutes before I was going to do that, I got a phone call. It was my boss, and he wanted the department chairs to meet today, okay, at 12:30. Well, I had class that went till 12:45, and I told him that, but he said that'll be fine and stuff like this. Then I found out we also had a faculty meeting today, or staff meeting, the whole college. That was at 2:30. Okay, so I had my 8:30 class, which he stayed on the phone until after 8:30. I kept saying, look, I've got class starting in 1 minute. I got class starting right now. I've got class starting. It's already supposed to be started. Finally, I got him off the phone so I could start my 8:30 class. And then in the 15 minutes between the first class and second class, I had a student who had questions, and I just couldn't believe it. We had gone this far in the class, November, middle of November almost, okay? Getting close to it anyway. And she still couldn't figure out where her ebook was. Now she uses the Cengage thing, and she was thinking she couldn't find things in the ebook, and I kept asking her questions. Finally, I found out she was in WebAssign, thinking that was her ebook. And I said, no, no, no. Finally got that done. That ate my entire 15 minutes between classes, so I was late for my second class. Okay. And then the second class got over on time, and I was able to start my third class on time. So that's 3 Zoom meetings. And then as soon as I got through with that third class, I went straight to the department chair meeting. That was my 4th Zoom meeting. And then I had time to eat a little bit of lunch and came back up here and had my faculty meeting that just is still going on, in fact, but I had already emailed the vice president and said I have a mini term 2 class that starts at 3:15. I've got to leave the meeting before then. So this is my 1, 2, 3, 4, 5, 6th Zoom meeting today. Okay, 4 of them were my classes, 2 of them were outside. That doesn't count the phone conversation that made me late for my first class, or the extra meeting that I had here. Now, something looks like it may be happening. Nope, we still got only 4 students here. Sorry about that. Okay. Now, why am I telling you all that? Partly because that 2 hours in the middle of the day, I would plan to finish typing your lab. I did not get it typed. Okay, sorry about that. I think we'll still be able to do the lab today, but you're going to have to just fill in a lot of gaps um, and send me the results. Okay, um, so sorry about that too. I think that's a better idea than me teaching all through 4.5 hours a day and then not having enough to cover in the future. So I think we will have lab today, but I do not have a lab out there for you ready to go because I've had 6 Zoom meetings today, and last night I was just completely out of energy and out of steam, and I guess I could have gotten it done, but I didn't know all this was going to happen today. All right. That said, do y'all have any gripes, problems, issues, concerns, questions? One more, I don't think I mentioned it before, but let me make sure you're aware of this. It's sort of a good news, bad news situation. The bad news is that tomorrow is a state holiday. Okay, the college will not be open. We will not have any classes tomorrow. Everything is shut down. It's Veterans Day. Alabama is one of the few states I know about that does count that as a state holiday. But the good news is it doesn't bother us, does it? Because we meet on Tuesday and Thursday. So we will meet on Thursday as normal. There won't be any classes tomorrow. Okay. Now, here is the other big issue. And this one is a big issue, and I think it will be a big issue for most of you. Okay? Have any of you registered for spring term yet? Yay or nay? No. Unfortunately, I think that's the common response. Now, I don't know why, but registration is way, way down. And that's what the phone call this morning before my first class and the meeting right after my third class were all about, is they are having next week, Monday through Thursday, all faculty that can be on campus have to be on campus. They're not teaching on campus, but they want them there for registration purposes. Well, number one, faculty cannot register students. When this new system came out, Banner, only students can register students. We cannot register you. But they want us all on campus for some reason to be there to encourage students to register. Okay? Now, I don't know if students are going to go to campus. So here's what I suggest to you. Register today. Register tomorrow. Register Thursday or register Friday. Don't get caught up in the mess next week, because it's probably going to be way too many people in way too small an area. They're going to try to keep social distancing and all like that, but it's almost a recipe for disaster. So if you can, register this week. Okay? If you can't, go on campus and register next week, or register remotely next week. But please, please, please register. Okay? Preferably before next week. And if you need to meet with someone, register on campus next week. If you can register without meeting with someone, please register remotely. Okay? Please do that. For your health, for the health of others, for the health of your family members, anyone else that you may, if you get exposed to something, take it home or take it somewhere to someone else. Please try to register as soon as possible and get that done. Okay? Now, that being said I think you probably have heard by now that there are going to be more on-campus classes in the spring than we had this fall. I think you also know that I will not be teaching any of them because I'm retiring on the 1st of February. So that's done. I'm not going to be on campus any more than I can possibly be. I've got to be on campus some to turn in keys, turn in computers, turn in a variety of things. So I'm going to try to get as much of that done before this term is over, so I won't be on campus with so many students or other faculty members. I want to time this so that I can have as few contacts as possible, because my anemia has just been horrendous this last couple of weeks, and I just don't need that exposure. So that being said, I will not be on campus much. I won't be on campus next week that I know of, and we'll just have to go from there. Was there anything else? I guess that's about it. Do you have any questions, issues, concerns, problems? Okay, just give me a feedback here. Would you rather register on campus next week or get it done outside of that? What is your feeling on it? Anybody have any feelings? It's not going to matter. Yeah. Uh-huh. Okay. Uh, um, right. Okay. Well, I appreciate that, and I understand that completely. So, I just I didn't know where students were on this. I just knew. You see, in the summer, which is when we first started this banner stuff, the new operating system, they were just all over the place with virtual advising, get virtual advising, and stuff like this. And I had just about every day was packed when I had available office hours for virtual advising. The vast majority of time, the vast majority of those 30-minute time slots were taken. This term, I've had 5 hours a week every week this term, and I have had zero sign up for virtual advising. Now, I don't know if it's just me. I don't know if my times are bad. Well, I am teaching just about all the time, but I have 5 hours every week, and so far nobody has signed up for virtual advising. Now, I have advised students. They've emailed me, and we've had telephone conversations and things like this, but virtual advising, zero. So I was wondering what in the world is going on here. I don't know if the virtual advising isn't working or they haven't put enough emphasis on it, but it's just I don't understand. It's nothing like it was summer, and we had pretty good enrollment in the spring and in the fall, but it's sort of seems like it's falling apart. All right, any other questions, issues, concerns, problems? I'm sorry I've taken way too long on this today, but I did want to clear the air on some of that. Well, here's where we left off last time. We're in chapter 4, heat and temperature, and the section that we're in now is a section 4.3, and its title is heat. 4.1 had been, just to catch you up on things, 4.1 was kinetic molecular theory. 4.2 was temperature. So even though the chapter is heat and temperature, we did temperature first and then heat. 4.3 was heat. We've done most of heat. We're now under heat flow. We did conduction as one form of heat flow. Conduction, remember, was heat that's transferred by contact. It's by mostly solids. Solids are fixed in their structure, crystal structure, so when one atom vibrates more quickly, kinetic theory of gases or of molecular theory, it makes the other one, makes the other one, makes the other one. That's conduction. Okay? Does most efficiently through free electrons. Those would be your metals. That's why metals are such great conductors. Not only of heat, next chapter, electricity as well. Metals are your good conductors. Okay? We did that last time. This time we're moving on to convection. And if you have your books, this is page 99 in the big books, 4-13 in the smaller books, and this is the right-hand column, convection. Now, convection is energy transfer through the bulk motion of the hot material, not just the free electrons, or not one molecule to another molecule to another molecule, another molecule. It's the energy transfer through the bulk motion of hot material. Now, what does that mean? Well, that means you're dealing with molecules that can move freely. In a crystal structure, molecules can't move freely. They vibrate and move to the next one, the next one, the next one, but that's all they can do. But when you are dealing with fluids, which are gases or liquids, that's where convection comes into play. Okay? And that's the materials that are most commonly use convection as their heat transfer. Okay? Energy transfer. If you're familiar with a space heater usually sits on the floor. You might aim it one direction or another, but it picks up cooler air and sends it out above. That's convection. Sometimes your gas furnaces, whether it's forced flow or natural convection, that's how they operate. If you have a gas furnace there, it pulls in cooler air from underneath the furnace, heats it up, and it moves into the upper areas. That's convection. Natural convection mechanism, you might use this term, hot air rises. Now, why does hot air rise? And it's not just air, same true as liquids as well. Why do hotter liquids move up, or hotter fluids move up? Because when you heat a fluid, that could be either a liquid or a gas, you speed up the molecules just like you did for a solid. But these molecules bounce against each other. They move further apart. That's why the density decreases, and therefore, since it's less dense, hot air rises. Now, in some parlance, different groups will say the chimney effect, and that's exactly what goes on with if you have a fireplace or anything like that, and you have a flue that's going up, the hot air is going up, the cooler air is coming in, you lose most of your heating up the chimney because the hot air rises. But that also keeps the smoke from coming in the room and the gases from coming in the room. You get your heat, and we'll talk about that next, from radiative effect. But that's also called the chimney effect. When I was growing up in Georgia, after my family moved to Burke County, Georgia, we at some point my father installed a wood stove downstairs and down in the basement. And what he would do, he would get the wood stove would just burn at low levels for a long time, and most of the heat was radiated out from there. We kept the stairwell door open, and when you walked down the hall past that stairwell door, you felt the heat just rising up the stairwell. Okay, and hot air was rising. And other places the cool air would be rushing downstairs, and that kept the whole house pretty warm. We used very little electric heat in cold weather. We used that wood stove, and it warmed the entire house. In fact, sometimes it would get so hot you'd want to close the doors because it did a great job of keeping it. And we had plenty of wood. We lived on the farm. About maybe 2/5 of the farm was wooded. We always had plenty of wood, and we went out there and cut wood all winter. Okay, not all the time, but when we needed it, there were plenty of trees that were down that we could harvest. So that's convection. Mostly fluids, liquids and gases transfer heat by way of convection. And for some reason, this PowerPoint will not advance. So here is the example. I don't know if you remember these, anybody? The good old radiators. But they're not really radiating as much as they're convecting. The cool air comes underneath. See all those flanges there? And it makes its way up, warming up as it goes, and then the warm air rises. It rises, gets further away, cools down, and circulates. So if you were ever in a classroom, I was in many old classrooms that had these convective radiators. There's no fan involved here. If you sat over here, you were toasty. But even if you sat over on this side of the room, you were warm enough, always. They always put these usually under the windows so that the colder side of the room was always plenty warm and everything circulated that way. That's convection. Now, I mentioned fluids do the same thing. For those who were in the the Physical Science 111 class, you know one of the effects of the seafloor spreading hypothesis was convection, which the hot magma came up to the surface and sort of drug the plates apart. That was one of the hypotheses of why there was this movement of plate tectonics. You've heard it there. Okay, for those who weren't in the class though, I can remember back decades ago, they came out with some glass cookware called visionware. It was usually a sort of an amber colored glass, and you could actually see through the pots and the pans. Well, if you ever watched that water in those pots when you're trying to boil something, like you're going to cook some beans or something like that, and you turn that on, you would watch the water go like this. Right over the eye, that was the hottest part, and it would rise there, get near the surface, cool off, move down the sides of the pot, and just keep doing that until it came to a boil. That was convection. Not just air, also any fluid, which would include liquids. Okay? Now, here's what's happening with that. This is sort of a strange illustration, but it's true. What happens is this air here is the same air, okay? And they're imagining a block of air here, a block of air here at the same temperature, okay? Well, they're going to heat this block and keep this one the same temperature. As they heat the block expands. Now, it's not a real block. Okay, here comes Jacob. Glad that Jacob could make it today. So now we're up to 5. We could field the basketball team if we needed to. Okay? Before 4 basically was a bridge table, was about it. Let me make sure that nobody else is in the waiting wing there. Nope, just 5 students, nobody waiting. But I'm glad y'all are here. Okay, so what they're showing here is at the same temperature, the same blocks have the same number of molecules. But if you heat up one of these blocks so it expands, hot air rises or expands, okay, then it still has the same number of molecules as this one. But then if you cut this down to size, the same as this one, it has fewer molecules in the same size block. So therefore, this is not balanced anymore. The hot air rises, the cooler air sinks. That to me is a strange illustration of what they're trying to say, but it is true. That is correct. Okay? Any question on convection? Okay, I can't get it to advance, so let me click on that. Now, the third type of heat transfer. And remember, heat is the transfer of energy. We had conduction, mostly solids. We had convection, mostly fluids, liquids, and gases. The third type is radiation. What's left to radiate? Well, pure energy. That's what radiation is. It's typically not the movement of molecules. Radiant energy is the energy associated with electromagnetic waves, not particles waves. Radiation can operate through a vacuum. Why? It doesn't depend on molecules. It depends only on electromagnetic waves. All objects emit and absorb radiation. I have a fairly high metabolism, always have had, and I can remember, especially shortly after we got married, my wife would say, "Can you move to the other end of the sofa? You're just radiating too much heat," because I just was always hot, okay, and in a heat sense anyway. Okay, so anyway, all objects either both emit and absorb radiation. I don't know why last night it was so hot. I had to even throw off the sheet. It was just that warm. I think we got up to pretty nice temperature yesterday and the house never cooled off. Okay, so all objects either emit or absorb radiation. Both emit and absorb. Now, what temperature determines is what is that emission rate. Okay, the house absorbed radiation yesterday when it got up to at least 78 degrees yesterday. It absorbed radiation, and then overnight it didn't emit as much as it had absorbed. So the house stayed pretty warm. And we're not that well of insulated house. Our house was built in 1930, so it's not that great of insulation, but we did maintain our heat energy, electromagnetic radiation. So the emission rate, the temperature determines that. The higher the temperature difference is between inside and outside, the faster the radiation rate. I've noticed the clock, it is a clock too, but right next to where my wife usually sits, she has a device that has time on it. It's a clock, but it also has, we have a receiver out on the side of the garage that measures outside temperature, and then the device itself inside measured the inside temperature. And every time I've looked at it today, it's been within a degree of being the same temperature inside and out. So our emission rate is very low today because the temperature difference determines that emission rate. Now, another thing that temperature determines is the intensity of the emitted light. Okay? And finally, temperature determines the type of radiation given off. Now, I would have turned some of these around and said these things determine the temperature changes. But they're talking about temperature determining these things. The higher the temperature, the greater the emission rate. And here comes Rucker. So let me get Rucker here. There he is. All right, we're up to 6. Now we got enough for a volleyball team. Okay. I hope we have some good servers. Okay. The intensity of the emitted light, if an object is very, very, very hot, then the intensity of the emitted light is much more intense. And also the type of radiation given off. The higher the temperature, the higher the type of radiation given off. Temperature is determined by the balance between the rates of emission and the rates of absorption. Like I said, today and last night, I can almost guarantee you this house anyway, has been it's been very balanced between the rates of emission and the rate of absorption. Now, let's talk about, I think someone was trying to get in, but I can't see who it is. Is it Daniel? I think it must be. Okay, now I'm just going to make a guess here. I'm guessing that the GM folks must have had, and here's Rodrigo. I'm really more convinced that the GM folks must have just let out from their previous class, because all 3 of the last few people were GM students, I believe. Is that not correct? Glad y'all could be here. Okay. The example they give down here is global warming. Now, this is going to take a little bit more background. I wish they had given us a little more background before they gave this as an example. But if you remember, I think it was in here that we talked about the radiation spectrum. Let me make sure. I've taught this class so many times I can't remember where this shows up in the book. I'm guessing we haven't gotten there yet. So we're going to get there in a minute. In fact, let's go on and get there now and come back to it. Okay, that sounded crazy, but nope, not here. Maybe it was the last chapter, was it? Chapter 3? Yes, it was. If you got your books open, go back to page 73, okay? And there you'll see the picture of the spectrum of energy coming from the sun, okay? And basically, just about anywhere, but this is what coming from the sun, okay? Now, I think I mentioned to you then, probably several times, that the sun is emitting enormous amounts of energy, incredibly enormous amounts of energy. And we are pretty far from the sun, and we're still getting hit by enormous amounts of energy from the sun. And we're 93 million miles away. So the sun is just constantly putting off energy, constantly. Okay, a lot of that energy is gamma radiation, which is deadly radiation. You don't want to be around that. Much of it is X radiation, which is very high energy, high power radiation. It also kills. Then you have what they call, and I'm leaving some out, but ultraviolet radiation. Now, ultraviolet radiation also is somewhat deadly, okay? It destroys tissue, okay? It damages tissue. It doesn't necessarily kill, though it has the capability of doing it, okay? Now, fortunately, our atmosphere, this cloud of air that surrounds our planet, blocks most of that deadly radiation. Just about all of the gamma radiation gets deflected, doesn't make its way through our atmosphere. Most of the X radiation gets deflected. It doesn't make its way through our atmosphere. However, a little bit of the ultraviolet radiation does come through, okay? And that's why if you're out in the sun too long, especially when you're very young and very, your skin and tissue and stuff is very tender, and you're in the sun too long, you can, decades later, develop things like skin cancers. I've had at least one removed already, have a couple of others that are close. I've had 2 cataracts removed. That's damage caused by ultraviolet radiation from the sun. And if you live long enough, you'll probably have cataracts removed as well. My skin, I have spots and blotches and things on my hand that, are caused by ultraviolet radiation hitting my skin. It destroys or damages tissue, okay? So our atmosphere is trying to keep most of that harmful radiation out. Now that narrow little spectrum, if you go back to the page I was mentioning before, it's called white light, okay? It's called the visible spectrum. It actually starts the violet, ultraviolet light goes into violet, then a color sort of indigo, bluish, greenish, yellowish, orangish, reddish, and then finally you get down to infrared. But that little spectrum that contains those colors, I'm going to start from the other end, red, orange, yellow, green, blue, indigo, violet. That's what our atmosphere allows in. And that's Pretty much all of it. Like I said, some ultraviolet comes in, and some below the red, you have what they call infrared. Infrared is basically heat. Okay? Now that's not quite a good definition because heat is a transfer of energy, but that's what's going on. That white light that comes through gets lengthened in wavelength, reduced in frequency, so now it gets trapped here on Earth as infrared radiation. Now some of that infrared makes it back out again, but most of it does not. That's why at our distance from the sun, 93 million miles away, even though we're getting bombarded with energy, we should be pretty cold. But our atmosphere acts as a big blanket for us and keeps us warm. Okay, now, here's what they're talking about here. The temperature determined by the balance is determined by the balance of the rates of emission and absorption. We absorb heat from the sun through the white light that comes in and through our a little bit of the others that come in. We emit light back, or heat back into the ether space, back out into the solar system. Okay, it just, some of it does lose. Okay, we emit it back out. Here is the issue with global warming. The gases that we have been increasingly producing, especially since the Industrial Revolution, when we started burning more fuels, burning more coal, burning more petroleum products, burning more natural gas. We just have been increasing and increasing and increasing our consumption of the fossil fuels. When you burn those things, you are also emitting carbon dioxide. When you drill for those things, you are letting methane and other gases like that escape into the atmosphere. And all these things are gases that trap more heat. So our emission rate falls, our absorption rate stays the same, and we get warmer. That's global warming. Now we call that the greenhouse gases. Why do we call it greenhouse gases? We have back in our backyard, I can't quite see it because it's on the other side of the garage, we have a little greenhouse. Now we don't use it most of the year, but when we do, in fact probably within the next few weeks, when we get that first major freeze, we will go out and put as many of our plants that we can't fit in our garage, we'll put as many as we can into the greenhouse. Okay, now that greenhouse is made up of plastic mostly, and the plastic allows the radiant heat to come in from the sun, radiation come in from the sun, but then when it comes in, it lengthens its wavelength, it becomes infrared or heat, and then it gets trapped in there because that's harder for it to get back out again, just like it's harder for us to emit once we've absorbed. Okay, now you all probably realize this by back in the summertime. If you drove to campus or drove anywhere and you weren't parked in the shade somewhere and you had all your windows up and you went back to the car a few hours later and had been sitting there in the sun, you know that steering wheel was hot. That seat was hot. It was probably 10 or 15 degrees hotter inside the car than it was outside the car. Why? Because the glass, the windows of your car, the windshield of your car, allowed that white light in, the radiation in, but when it did, it lengthened its wavelength, dropped its frequency ever so slightly, and therefore it became infrared rather than white light. It became infrared radiation, which could not escape because it didn't have enough energy to get back through the glass. That's what global warming does. Our atmosphere acts like that glass and warms us up because we have too much carbon dioxide, too much methane, too much there are some others, molecules in the air that do change the rate of emission and absorption. They let enough come in but don't allow enough to go out. And that, folks, is what's happening. And that's why one reason it's really going to be important for this new administration coming in, which I hope they get there soon. Can't be before January, but they're going to get us back on the climate the Paris climate agreement and those kinds of things, because we are in danger of destroying parts of our environment because of global warming. We may already be past the point, but maybe we can extend things for a little bit. Okay, that may be too much, but I said it. Okay, that's radiation. Now we move on to section 4.4, heat, energy, heat, and molecular theory. Now we've already been talking about this to a certain extent. There are two responses of matter to heat. One is, as the matter heats up, its molecules move faster, its electrons move faster, something moves faster, and it increases the temperature because the average kinetic energy of those molecules is what makes temperature. Okay? So that temperature increases within a given phase. Now what does that mean? That means if it's a solid, the temperature goes up. If it's a liquid, the temperature goes up. If it's a gas, the temperature goes up. A temperature increase within a given phase. The heat goes mostly into internal kinetic energy. That's what changes the temperature. That all depends on what we talked about in the last class, specific heat. And that's part of what we're going to be talking about in today's lab, specific heat. That's one response of matter to heat. It goes up in temperature based on that specific heat. Now let me remind you, okay? Specific heat is the amount of heat it takes to raise the temperature of 1 gram of material 1 degree Celsius, okay? That's what we mean. So the more heat it takes to raise the temperature, that's a higher specific heat. The less heat it takes to raise the temperature of the same amount, that's a lower specific heat. So remember that. It's a little backward seeming. The more the temperature goes up, the less the specific heat is. Okay? Hang on to that concept. Here's what's happening there. Okay, here we have ice. That's a phase. That's solid water. Okay? That ice being a solid, it's in a fixed crystal structure, and all you do is increase the vibration. When you add energy to it, you increase the vibration, you raise the temperature of the ice. Well, does that mean the ice melts? That looks like it's melting, and maybe it is, but they should have this so it's not melting. Now, I don't know if you've ever done this before. You've reached into the freezer of your refrigerator to put some ice in your glass. But shortly before you did that, you weren't thinking about it too much. You may have washed your hands so you wouldn't get the ice dirty or whatever, but you may not have dried them completely. And if you left a little bit of moisture on your hand, you reached into the freezer to get ice out, you could hardly get it off your hand because it froze to your hand. Because the ice was below the freezing point, and rather than melting, it was increasing in temperature, but it was freezing the water that was on your hand. And that's surely what's happening. Now, if you had, now that looks like ice water, which if it is, that's sort of not the best illustration here. If that's just water, and that's what they're indicating here, it's just water, then as this warms up, it just increases the movement of the molecules. Now remember, over here when it's ice, all it can do is vibrate, but it vibrates faster, raising the internal energy of the water, the internal kinetic energy of the ice, Here you're increasing the internal energy of the water. You're increasing the temperature of that water. Okay? Over here, it's already gas. And what happens when you increase the temperature of the gas? It moves faster. They move further apart. It expands. It convects. Okay? It's getting bigger. Okay? Lower density because it's taking up more space. Okay? That all depends on specific heat. Specific heat for ice was 0.5. Specific heat for liquid water was 1.00, just about the highest material specific heat we've got going. The specific heat for water vapor, 0.48, almost the same as it was for ice. Okay? The more you increase the energy, the faster the vibrations, the more you increase the temperatures. Now, what's also included here is what's going to show up next. And that's why I said this isn't really the best slide here. Because if you were to decrease the molecular potential energy here, this ice, the water vapor here, slows down. At some point, it condenses. And that's what they mean here. It's going from a gaseous state to a liquid state. If you further decrease the temperature so that the water is getting colder all the time, at some point it actually freezes, which releases energy. Okay? Melting, which is showing here, is actually increasing the energy of the water molecules. And if this is indeed ice water, all you're doing, you're not changing the temperature, you're melting the ice. Okay? But then when it all becomes water, you increase the water temperature until it starts evaporating, and then you have a change of phase. So what they're talking about here is temperature increases within a given phase. That's why if this is very cold ice, none of it's melting, sticks to your finger, that kind of stuff, that's increasing the temperature of the ice, increasing the temperature of the water, increasing the temperature of the water vapor. That's what happens when within a given phase you add more heat. Now, the second issue here, the second response of matter to heat is a phase change. Okay? But the phase change occurs at constant temperature, not at changing temperature, at constant temperature. You had changing temperature when you were dealing with specific heat. You have constant temperature when you're dealing with what they call latent heat. This is related to changes in the internal potential energy of the molecules, not the average internal kinetic energy of the molecules. Now, and that latent means the same word, about the same meaning as the word hidden. This is hidden heat. Okay? Heat that you don't see a change of temperature, but you know things are heating. Okay? Now, let's see where the next slide is going. We're going to get there in just a minute. So let's go back to this slide. When it was changing from a solid to a liquid, that was at a constant temperature. When it's going from a cold solid to a warmer solid, no melting occurred. You were just changing the average kinetic energy of those molecules, so the temperature was going up, maybe from minus 8 degrees Celsius to minus 2 degrees Celsius. That's a change of temperature without a change of phase. It's still ice. That's when you put your hand in there, it sticks to your finger, you can't get it off. It hurts when you pull it off. Did any of you see the old movie, goodness gracious, I can't think of the name of it, but when the little kid stuck his tongue to the flagpole, metal flagpole, and it got stuck there? Say that again? Yes, it's a Christmas movie. The Christmas Story or Christmas something or another. It was a Christmas movie, sort of an old one. Actually, I've heard another version of this, and this one I know was true, or at least who I heard it from, I believe. My wife's brother is 4 years younger than she is, so she wasn't present to see this, but she heard about it big time. The next was her sister, who was 2 years younger than her brother. And her mom had taken the two younger kids to the grocery store and was rushing around getting the groceries. And she was just about ready to leave, and there, her youngest daughter, Terry, was there. She said, "Terry, where's Keith?" She said, "Well, he was back in the back." "Well, go get Keith." So she sent him back to the back to get Keith. She was ready to check out. And Keith was back there. It was a hot summer day. And Keith was, oh, let me tell you this. Keith was Mr. Cool. Now, he was a young kid there, but he still thought he was Mr. Cool. And he usually was Mr. Cool. I mean, he was a good-looking kid. He was a pretty bright kid. Just had everything going from him. He was top of the world in his mind. Well, he saw the freezer unit there where you could just reach in and get things. It had this layer of frost on it because it was open. And he thought, "Oh, it's hot today. Boy, that looks like that would be so cooling." So he, sure enough, got his tongue down and went to lick the ice. Okay? But the ice was pretty cold ice. It wasn't near the melting point. So when the saliva from his mouth hit that ice, it froze, just like the kid's tongue did to the flagpole. And he couldn't get away. And Terry went to say, "Keith, Mom's ready to check out. We need to go. We need to go." He said, "Huh, huh." You know, he could hardly speak. His tongue was stuck. "Go get Mom." You know, she finally figured out what he was saying. She went to get Mom. His mom was so embarrassed that her son had his mouth stuck to the freezer, and she just yanked him by the collar, pulled it off, left some skin on the ice, you know, and his mouth just started bleeding like crazy, crammed a Kleenex or something into his mouth, and chased him out of the store. She went on and maybe she had already checked out the groceries, and she just got him out of the store before anyone found out about it. So Mr. Cool was a bit too cool that day. But anyway, that's what happens when you raise the temperature but don't change the phase. Okay? But when you raise the temperature up to the freezing point, then melting occurs. And guess what happens when that happens? No change of temperature. If you have a glass of ice water, and if we were on campus, we would have already done this lab probably. You put a thermometer in that ice water, it's going to read very close to 0 degrees Celsius or 32 degrees Fahrenheit. It's going to sit there. It's going to sit there at that temperature until every bit of that ice melts and becomes liquid water. Once all that ice is melted, then you see the temperature start going up. So when you have a change of phase, you have no temperature change. When you're boiling that water to make your iced tea, to make your tea, or to boil your beans in, or whatever you're doing with it, once it starts boiling, before it boils, you're increasing the temperature. But once it starts boiling, the temperature is fixed there at 100 degrees Celsius or 212 degrees Fahrenheit. That's the boiling point of water. It stays at that temperature until every bit of that liquid water evaporates and becomes gaseous water, water vapor. Once that happens, then this water vapor can increase in temperature. But within a phase, it does not change. Within a phase, it changes its temperature, but not the phase. In between the phases, it changes phase, but not the temperature. Okay? Let's see who this is. I can't see. Let's see who it was that just came in. Got Rucker, Amia, Angelita, Daniel. I think it was Dre. Dre, you just got in? So let me mark Dre here, and we're up to 1, 2, 3, 4, 5, 6, 7, 8, 9. Got enough for a baseball game now. Yep, 10 participants, okay? So that's what's happening when you change temperature, use specific heat. When you change phases, use specific heat. You use latent heat. Okay, so let's go. I can't get it to advance. Okay, there. So here's what we mean when the ice is down there at maybe minus 20 degrees. Don't stick your tongue on that one. Okay, minus 20 degrees Celsius, which is below the freezing point, and you add heat to it, you actually increase the temperature of the ice without melting the ice. That's like your wet finger when you go and pick up the ice cube to put in your glass and you can't get it to come off your thing. You are still at you're changing the temperature of the ice but not melting the ice. But then you add more heat to it. Once it reaches that 0 degrees, that's called the melting point or the freezing point, depending on which way you're going with the heat, then it stays at that 0 degrees until every bit of the ice melts and becomes water. Once it all becomes water again, now you start increasing the temperature of the water. That's okay. This is specific heat of the ice. This is latent heat of the ice to water. This is specific heat of the water. This is latent heat of boiling. Again, when you reach that 100 degrees Celsius, the water starts boiling, and it doesn't do you any good to keep the gas up on it, to increase the electricity under the eye. Once it starts boiling, you can cut it down, okay? Because it's not going to change temperature until every bit of that water is boiled away, and then you start burning things because now you're warming. The water vapor is all you're doing, and whatever is in that pot is now getting annealed to the pot, okay? The specific heat here, that's the slope here, is 0.48. The melting point, no change of temperature here. The specific heat for liquid water, 1.00. I said that wrong. This is 0.5. This is no change of temperature. This is 1.00 specific heat here. No change of temperature here. Change of phase, but not change of temperature. And then that steam, it increases at 0.48. That's specific heat of warming. Now, what are those latent heats? For water, melting or freezing, whichever way this is going here, this latent heat is 80 calories per gram, no degree Celsius because there's no change of temperature, 80 calories per degree. No, I'm sorry, per gram, okay? Specific heat here is 0.48 calories per gram degree Celsius. This is 80 calories per gram. This is 1.00 calories per gram degree Celsius because you are changing temperature here. This is 540 calories per gram. That's an enormous amount of heat. Boiling water takes a lot of heat, okay? And that's why steam can burn you so badly, because you don't just have the temperature, you also have the change of phase. So that's a lot of heat being given off. And then once it becomes steam, then you can warm it up at 0.48 calories per gram degree Celsius, because here you're changing degree Celsius again. I'll show you those formulas in a minute, okay? No, let me also say this. If you went the other way, same thing happens. If you cool water vapor, then it comes down in temperature according to specific heat, 0.48 grams calories per gram degree Celsius, until it gets down to the, and you could call this, they call it the boiling point this way, you can call it the condensation point this way. Now, I don't know if you've noticed this before, but in the summertime, you pour you a glass of iced tea or ice water or something, you set it down on the table, and immediately you get water droplets on the outside of the glass. Is that glass leaking? No, it's not leaking. What's happening, you're condensing that water vapor that's in the air because it gets close to the glass that is near the freezing point down here, and you start condensing the water on the outside. Okay, so this is either the boiling point going this way, the condensation point going this way. Specific heat here, latent heat here, latent heat of vaporization is what they call it. Okay, then specific heat of liquid water here, and this is the latent heat of fusion here. Freezing going this way, melting going that way, we call it latent heat of fusion. Okay, so it works when you're going this way, it works when you're going this way. It's just changing the phase, dropping the temperature, increasing the temperature, changing from solid to liquid or liquid to solid, changing from liquid to gas or gas to liquid. It just depends on which direction your heat is going. This is showing heat input. It could just as well have been heat loss. Okay, so here are your phase changes. The latent heat is the heat of fusion when it's going from a solid to a liquid or a liquid to a solid. It's the latent heat of vaporization when you're going from a liquid to a gas. They also call it the same when it goes from gas to a liquid. Though that, well, actually, they call that condensation now. Okay, and there are some materials that go straight from a solid to a gas or from a gas to a solid. That process is called sublimation. Have any of you ever heard of dry ice? Yay or nay? Okay. Where have you encountered dry ice? Maybe not directly, but indirectly. Okay, say that again. You had a what in your stomach? Oh no, that must have been incredibly painful. Okay, not really? Okay. It does warm up quickly, but when it does, it goes straight to a gas. It goes straight from a solid to a gas or a gas to a solid. Now, what you do with this, when I was in between jobs after I got laid off at Southern Research, when Congress changed from sponsoring research from outside sources and made EPA do all their own research, our group that did radon research got let go, the whole group of us. And it was not a good time to do that. And I got a job, sort of a part-time job, taking some soil samples over near Anniston, Alabama, where the former Monsanto plant had polluted the soils and the waters really, really badly by dumping stuff into the environment. So we were taking soil samples there from various neighborhoods to and just all areas around to measure how far the pollution went. And we had to send the stuff in with packed in dry ice to keep it as cold as possible. Okay. Now also, if you've ever been to a rock concert and seen the steamy looking atmosphere they have sometime, that is because they've exposed dry ice to the concert venue, and now the coldness of the dry ice going from a solid to a gas that's releasing an enormous amount of energy or absorbing an enormous amount of energy, it changes the water vapor in the air to water vapor to water droplets. So actually what you're seeing are clouds, and they use various lights and stuff to make it look really cool, and it is pretty cool. Okay, that's sublimation, and whichever direction you're going, that's what they call it. Most materials go from liquid to gas or solid to liquid. They don't go from solid to gas, but certain things do at certain temperatures and pressures. Okay, so when the temperature goes from a solid to a liquid, that's called the melting point for that material. When it goes from a liquid to a gas, it's called the boiling point. And of course, when it goes to a gas to a solid, it's called the sublimation point. When it goes the other way, that you're dropping in temperature, and it goes from a gas to a solid, which is not an easy thing to do, that's also sublimation. When it goes from a gas to a liquid, that's condensation, which we were just talking about, the condensation point. And when it goes from a liquid to a solid, that's called the freezing point. Now guess what? The melting point and the freezing point for a given material, exactly the same temperature. These are temperatures. This is the process: fusion, vaporization, sublimation. Now they name all three of these sublimation, so that makes it a little confusing. But when you're going from adding temperature and going from a solid to a liquid, that's called melting. From a liquid to a gas, that's called boiling. When you go the other way and go from a gas to a liquid, that's called condensation. And when you go from a liquid to a solid, that's called freezing. The temperature at which these happen are all the same. Okay? It's just which way is the direction going. Is it getting warmer, adding energy, losing energy? Okay. Now, I promised to give you the formulas, and they didn't show them in the PowerPoint. So let me go back and show them to you here. I think maybe this is the best place to do it. Let's see if there is a better place here. Okay, let me do this one here. That's probably a little cleaner area. Okay. This happens when you increase the temperature within a given phase. It's also decreasing temperature in a given phase. The heat goes mostly into internal kinetic energy or from the internal kinetic energy. We've already had this formula here, and what I need to do is probably change the color of this. Okay, because this is red. I'm going to change it to the bright yellow so it shows up better on the screen. This is Q, that's change. I'm going to put delta Q, change of temperature, no, change of heat. This is heat, not temperature. And this would be C M delta T. C is specific heat, M is the mass, and this is change of temperature. Okay, and this is change of heat. The heat transferred. Q is equal to Cm delta T. Now, the C, let's just take for water, is when it's in a liquid phase, it's 1.00 calories per gram degrees Celsius. Okay, if that C is ice, that's 0.50 calories per gram degrees Celsius. If that C is steam for gaseous, that's 0.48 calories per gram degrees Celsius. Okay, now this is all H2O, liquid water, solid water, gaseous water. That's what you deal with anytime you're changing the temperature of a substance within a given phase. This would be when it's liquid phase, that's when it's solid phase, if I could get my pen to show up, and that would be gaseous phase. Okay, now, what if you have a phase change at constant temperature? That's latent heat. Okay, so there your formula is change of heat, because you've got to have a change of heat for it to happen, is equal to L M. No delta T involved here. This is latent heat and this is your mass. Okay, now if this is a latent heat of fusion, that's going from a liquid to a solid or a solid to a liquid, same latent heat. For water, going from ice to liquid water, or liquid water to ice, this is 80, I think it's 0.0 calories per gram. Notice there's no delta T here. If, however, this is going from liquid to gas, then your delta Q here is the latent heat of vaporization, L sub V times M. This L sub V is 540.0 calories per gram. So you see, it really makes a big difference. Enormously large latent heat here. A large latent heat here, specific heat, relatively small. Okay? The formula is given in your text, but they usually list the L first. So they put it this way. Said the delta, they just say Q is equal to MLF. That's fine too. That was mass in front and latent heat here. Or they call this one, and it doesn't matter, you can put it in any order you want to, M times LV. Now, since they did specific heat in front, I put latent heat in front. It doesn't matter. Okay? Now, let's move on to, we've already hit that slide, and we've hit that slide. Okay, before we get to evaporation and condensation, there is a pretty good blurb on page 103, the entire page. It's called A Closer Look, and it's looking at some of your passive solar designs. Now, we talked a little bit about this both in the last chapter and earlier in this chapter. Why they put it here rather than the last chapter, I'm not sure, but that is a whole page of some of these designs, and well worth your read. Okay, now somebody just made a noise. I don't know what that was. Let me make sure there's no students coming in. No, we still got just the baseball team. So 9 students here. Okay, so that's well worth a look. I kind of drive my wife crazy sometimes, though she's finally gotten used to it, I think. I go through every morning, and in the rooms that she's not too much interacting with, I open the blinds every morning in the winter time to let as much sunlight come in to get passive solar warming. But in the summertime, I turn the blinds up as far as I can to keep the sunlight from coming in, that radiative energy from coming in, to keep the room as cool as possible. Okay? And I go through and do it. Now, on the north side of the house, where the direct radiation doesn't come in, I just open them maximum amount to get the most light coming in. Okay? Because it never comes in the radiative effect. So in some senses, I'm doing what they call passive solar design, and they show several of these here, and greenhouses are one form of passive solar design. Okay, so I just wanted to say that. Now, when you turn over to page 104, you will see the table that gives those same numbers I did, and here it is. These are the latent heat that you deal with, well, all the heats. This is the, I can't read that, the specific heat for water, ice, and steam, which we talked about. This is the latent heat of fusion, I think it is, yes. Here's the latent heat of vaporization, and the following, the last one there is, excuse me, sorry. I don't know why those just come on unexpectedly. Maybe it is cooling off a little bit outside. Like I was saying, we had been almost at equilibrium all day long. It may have dropped a little bit in temperature. The mechanical equivalent of heat, if you remember, I don't know why they use kilo on one and joules on the other. 1 calorie would be 4.184 joules, 1 kilocalorie would be 4.184 kilojoules. Okay, those numbers are close to each other. They have the same prefix, but they put 1 in kilocalorie and 1 in thousands of joules. Why they do that, I don't know. Okay, but they do. But both of those are correct. Okay, now before we move to evaporation and condensation, we do have, I can't get my thing to advance or retreat. So let's go back here and do clear my screen here so we can do example 4.7. How much energy, okay, where am I going to write this if I can get my pen to show? There it is. Energy is Q, okay, heat energy we're talking about. Does a refrigerator remove from, so this is the unknown here, we're looking for the Q, okay, or delta Q I like to call it. Remove from 100 grams of water. So this is 100.0 grams of water. Okay, well that's obviously a mass of water. Okay, at 20 degrees Celsius, so 20.0 degrees Celsius, that is the initial temperature of that water. Okay, to make ice, so it's going to, and by the way, 20 degrees Celsius is right around room temperature, right around 68 degrees Fahrenheit. Good, comfortable temperature. You just turn on the faucet and that's what you got, room temperature water. Okay, to make ice at, so this is going to ice, not liquid water, ice at negative 10 degrees Celsius. And that would be your final temperature of ice. Now that's not your delta T, okay, just warn you that. You have to be within a phase to have a delta T. That is a delta T, but it's within 2 phases. Okay, what you're doing, you're starting with water, liquid water, at 20 degrees, and you've got to drop that to 0 degrees, the freezing point of water. Okay, so we're going to start with a delta Q to cool the water. Okay, so that's what that stands for. Well, that's going to be, if you remember, if you have a change of temperature, which you have, going from 20 degrees down to 0 degrees. Okay, that's your final temperature of the liquid water. Okay, so that's going to be Cm delta T. That formula I gave you just a little bit ago. You're changing the temperature within a given phase, liquid water here. Well, your C here is 1.00 calories per gram degrees Celsius. Okay, and your M is the mass, 100.0 grams of water. Okay, I'm going to leave off the water because I don't have enough room. And your delta T, you're dropping from 20 degrees Celsius down to 0 degrees Celsius. So the delta T is 20. T final minus T initial, actually your final is less than that, but we're going to leave it as a positive number. That's 20 degrees Celsius. Okay, so your degrees Celsius goes out, your grams go out, and that leaves you just with calories. So 1 times 100 times 20, that would be 2,000. 2,000 calories, little c calories. That's the heat that it took just to cool the water from 20 degrees down to 0 degrees. But you're not there yet. You've now got to make that liquid water into solid water. So that's going to be a delta Q of freezing or fusion. And that formula is L sub F times M. Remember, there's no change of temperature here. It's just the mass and that. Well, what's your L sub F? For fusion, that was 80.0 calories per gram. Multiplied by that same mass of water is now changing to ice. So that's going to be 100.0 grams. And notice your grams go out here, and that leaves you a delta Q of in calories. So that would be 8,000 calories. Okay, 2,000 calories to cool the water down to the freezing point, and another 8,000 calories to freeze the water down and make it go from a liquid to a solid. Okay, well, that's just the second part. Now you've got ice that's frozen at 0 degrees. Remember, you didn't change temperature here, 0 degrees, but you want to cool that ice down to minus 10 degrees. So you go back to the same formula you had here. This is the delta Q of cooling the ice. This was cooling water. This was freezing the water. This is cooling the ice. So that's going to be C M delta T. Well, the C for ice is 0.5. I think they may put another 0 in there. Calories per gram degrees Celsius, because you do have a change of temperature here, times your mass is that same 100 grams. Okay, times your change of temperature. You went from 0 here to minus 10 there. That's a drop of another 10.0 degrees Celsius. And again, the degrees Celsius goes out, the grams to go out, and now you're left with half of 1,000, which is 500 calories. So how much energy did it take to do that? You had 2,000 calories here, 8,000 calories there. That makes 10,000 calories plus another 500 calories. So 10,500 little c calories. If you think that number is too big and the unit too small, you can change that to 10.5, moving the decimal 3 places. 3 places means kilocalories. Now, if you were doing this with food calories, that would be 10.5 food calories, okay, but we're not. We're doing the other. Okay, what you get, 10.5, they say times 10 to the third calories. I just called it kilocalories. Now, they put an extra 0 on here, and why was that true? Well, because they had 4 significant digits here. I only saw 3 significant digits there. So I wonder where they got their 4th digit. That's why I rounded to 3. But they have 3 here, 3 there. There's another 3. 3 there. That's all we got. 3 there. That's all we got. 4 there. Yeah, we got that one. So actually, not all of those are significant. So anyway, they put an extra 0. I don't think it's justified, but same difference. Okay. 10.5 kilocalories, or 10.50 times 10 to the third calories. Any questions on example 7? I thought that was a really good example. It showed the specific heat of water, the latent heat of going from water to ice, and then the specific heat of going from 0 degree ice to minus 10 degree ice. Okay, so let's move on to evaporation and condensation. Now, you may have wondered about this. I remember wondering about it too. If I were to put a pan of water just out on the counter, if I'll leave it there long enough, the water is going to evaporate. Now, we didn't get anywhere close to the boiling point of water, so we did evaporate water even though we weren't at the boiling point of water. Similarly, that iced tea glass, remember, that you put out there, and as soon as you set it down, it starts condensing. Well, you might argue that yes, you are below the heat of vaporization, so you can condense, but it doesn't have to be, okay? The reason for this is individual molecules can change phase at any time because the individual molecules can be at varying temperatures, okay? And all that matters is what temperature you're at. I'm going to scoot backwards for a while. I hope I can get there. Hang on to your hat. This is going to go pretty fast, okay? This was back last time we talked about that. This. It may not show up here. I thought it would. No, it isn't. Let's go this way. Sometimes things will show up coming this way. They won't show up going the other way. There it was. There it is. Okay? This is a gas. This is air. Okay? Some of this air is down here at very low rates of speed. Some of it's up here at very high rates of speed. Most of the molecules are right along in here in the middle, and that's the temperature of the gas as we feel it. But some of those molecules are much colder, some of them are much hotter. So it's not at all surprising that maybe water vapor up here, a water that would be somewhere in here, would vaporize here, even if it's not, the average temperature is pretty low. It's also possible, not very likely, that things could freeze here with the average temperature being much warmer. Because in a gas, especially in a gas, you have a wide variety of temperatures of individual molecules. Distribution of the molecular speeds, which is related to the temperature of the gas, the average kinetic energy of those molecules. Okay, so let's go back to where we were, and that was quite a bit further. La da 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 da. Okay, here we go. Individual molecules can change phase at any time. That's why that pan of water just sitting on the counter, some of those molecules will get enough energy to vaporize, even though the temperature of the whole water is nowhere close to the boiling point. The internal energy of that molecule is enough to vaporize. So evaporation is the energy required to overcome the phase cohesion. That water that was in the pan at normal temperatures, is some of that will evaporate, especially if the air is very dry. Okay, if the humidity in the room is very, very low, more of that water will evaporate. And that's another issue, but it will happen that way. If you are out west, where you have out in the desert, you are going to probably feel pretty miserable because we're used to high humidities, and we're just used to those high humidities. You go out there where the humidity is very low, your lips will chap, your face will crack. I mean, all sorts of things happen because you're not used to that low humidity. Those people come here where they're used to low humidity. They come here and they feel like they're suffocating because we have such high humidity here. So that's also entering the picture. The higher energy molecules near the surface can escape, and when they do, it actually drops the average kinetic energy of that liquid. Okay, so therefore, well, I'll talk about that in a minute. Condensation goes the other way. The gas molecules near the surface lose kinetic energy and become liquid rather than gas again. They merge back into the liquid. That's if it's very, very high humidity, you can actually increase the water molecule in that space, especially if the space is a little cool. So here is showing, and they don't have this quite right, but it's okay. The lower energy molecules you would expect would be near the bottom, the 5s down here. And on average they are. Then your 10s are here, your 15s are here. I would think they'd be higher up. Your 25s though are near the surface because they're higher energy. This is just indicating the relative kinetic energy. Okay? And these are really much more kinetically active than these are. So therefore they have more, they contribute more to the temperature. Well, what's the average kinetic energy here? Before they escape, this would be 25, 50, 65, 75, 85, 95, 100, 105, 110, 115. So the total kinetic energy would be approximately 115. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units there. Divide the 115 by 10. Your average kinetic energy is 11.5. However, these near the surface at high energy levels, moving faster, if those do escape, you've lost those two. What do you have now? 15, 25, 35, 45, 50, 55, 60, 65. 65 is your total kinetic energy divided by 8. That's going to be something just a little bit more than 8. And that's what you got here, 8.1. 65 divided by 8, 8.1. Your average kinetic energy dropped from 11.5 to 8.1. That cooled the entire beaker. Of course, you lost a little bit, but it did cool it. Now, I've never had these or operated with them. They usually do them more out west than they do here where the humidity is lower. But hikers that like mountain climbing and that kind of stuff sometimes will carry their water in canvas bags. Well, those canvas bags actually let a little amount of water escape. And when it does, it's the high energy water near the surface. So the average kinetic energy is less. So when you drink the water out of those pouches, okay, those bags, it tastes cooler because you've lost your high energy water and the average kinetic energy is less, meaning the temperature is less. If you try that here in the southeast, that's going to taste like tepid water because you have high humidity on the outside, high humidity inside. You're not going to cool that much because not that many molecules escape because you have high humidity everywhere. Okay, but that's what's happening with evaporation. With condensation, the gas molecules near the surface lose kinetic energy to the liquid and become liquid themselves. These were gas molecules originally, they become liquid molecules. Okay, so there's evaporation and condensation. Now, the picture they showed in the book is one of Listerine. And if you've ever remember tasting Listerine, that's mostly alcohol, okay? Alcohol, you can see those droplets have formed on the inside of the bottle because the glass or the plastic probably is at a lower temperature and the liquid drops escape and then recondense near the surface. Okay, now flip to the next page and we are beginning 4.5, which is thermodynamics. Now my watch was running low on battery. I had to put it on charge. I don't have a good sense of what time it is. What time is it? Well, I've got that we've been going about an hour and a half. We go about 2.5 hours. So is that about right? We got an hour left to go or less than that? Everybody's asleep. Say again, a little bit less than an hour. What time is it now? No, what time is it now? 4:54. So we go until 5:45, so a little bit less than an hour. That's what I wanted to know. So now we're in 4.5, which is thermodynamics. What this is the study of heat and its relationship to mechanical and other forms of energy. The thermo means heat. Dynamics means changing. The changing of the heat, that's the study of heat and its relationship to other forms of energy. It's either mechanical energy becoming heat energy becoming mechanical energy, potential energy, one way or another, there's changes going on, and it's heat changes. The thermodynamic analysis includes your system. Okay, let's say that LED light bulb up there. It's producing light, it's producing some heat, but not nearly as much heat as the old incandescent light bulb that used to be there. Even less heat than the complex fluorescent. That would be the system. What is our system built up of? Well, so not only the system, it's also the surroundings, everything else around that. If I were to feel of that globe that's up there, I'd probably feel a little bit of heat. If I were to feel of it back when I had a complex fluorescent in there, it may have been just a little bit hotter. But if I felt of that globe back when it was the incandescent light bulb, that globe would have been hot. The light bulb would have been very hot. The globe would have been plenty hot. That's the surroundings, everything around the system. Now, thermodynamic analysis includes internal energy, the total internal potential and kinetic energy of the object in question. But we're less concerned with that than we are the external energy, because thermodynamics usually refers a bit more to external than internal, but it does include the internal. See, the system is mostly external, the surroundings are mostly external. It also influences or is concerned with some of the internal energy going on. So how does the energy convert? Well, one way that's always kind of a bad way, not always, but kind of a bad way, is friction. That converts mechanical energy into heat. I don't know if any of you have ever changed the brake pads on a car. If you did not want to do that right after you had run the car. Because if you had used those brakes very much and you went to change those pads, you burned your hands, guaranteed. You usually like to let those cool off for a few hours at least before you start changing them. Okay? Because that's what your brake pads are doing. They're applying friction to the brake drum and the brake pads, and those are heating up like crazy. Take your two hands, push them against each other and rub them together. You'll feel the friction. It's heating up. Okay? That's what friction does, converts mechanical energy, the energy of motion, to heat that you can feel there. Okay? Now, what is a heat engine? It's a device that converts heat into mechanical energy. It's exactly the opposite of this, friction. Well, that's your automobile, most of your automobile engines. That's taking heat from the explosions that are happening. You GM guys can explain this better than I can. In your piston, you are igniting with the spark plug, or if you're diesel, it's an automatic combustion there, just from the pressure. But you're igniting that with the spark plug, setting off an explosion inside your cylinder, inside the cylinder, pushing the piston downward. That is taking heat energy of that explosion into mechanical energy of turning your crankshaft to move your car. Okay, that's a heat engine. Device is converting heat into mechanical energy. Now, there's all sorts of other applications of thermodynamics here, of energy conversions. One of these is a heat pump. That's what we've got up in our attic in the upstairs part of the house. We have a heat pump. What you're doing with that, the first step, and it's actually the same for refrigeration as well, okay? What the first step is compressing a gas. That gas is usually used to be called Freon. They don't use Freon anymore. What do they call them now? R112 or some sort of refrigerant that they use there. That's the first step, is compressing it. Okay? Now, about this time of year, a little bit later, when you compress that gas, it produces heat. Okay? And that you take that heat and blow it across your coils and circulate that, and that's what gives you heat from your heat pump. If, however, it was the summertime or downstairs in the kitchen where our refrigerator is, what you do next is you compress the gas, but then you blow off the heat from that compressed gas, that refrigerant that you have. And then you let the refrigerant expand quickly, because when you compressed it, you made it into a smaller volume. When you let it expand quickly, it then went to a larger volume. When it does that, it absorbs heat. And that's what your refrigerator does. That's what your air conditioning does. That's what your freezer does. It is that expansion of the gas rather rapidly is what causes the cooling process. Okay? Now, even organisms. You are a heat engine. What is your temperature? 98.6. What's the room temperature? 70. You're much hotter than the room is. Why? Because you're an organism and you are metabolizing food as you're sitting right there where you are. You're burning hydrocarbons, carbohydrates, and you are producing heat. Okay? You're also doing electrical signals that allow you to see, to hear, to speak, to do whatever. You are an organism that is doing energy conversion all the time. How many hurricanes have we had this year? We're up to at least 8 now. We went through the 20 some odd letters in our alphabet. I don't think we hit them all, but we hit a lot of them. And then we went to alpha, beta, gamma, delta, and somewhere down the line was eta. That was the last one I remember. So we're probably close to 30 hurricanes or tropicals, named tropical systems this year. What are they doing? They're absorbing energy from the equatorial regions. That's an energy transfer, moving it into the temperate regions, that's where we live, and dumping that energy here. Thank goodness it's happening, otherwise the planet would overheat in the equatorial areas and freeze to death in the polar areas. Hurricanes are big heat engines that move that heat from the tropical areas up to the polar areas. They probably don't get all the way up there, but the remnants do. What are stars? Stars are enormous heat engines. You're fusing hydrogen into helium, fusing helium into carbon, fusing carbon into higher density molecules or atoms up to iron. Okay? Those are enormous heat engines. Okay? Black holes. Now, we don't know what black holes are doing. They're just sucking up all the energy they can get, period. So those are enormous energy sinks. They're just sucking in like everything. Virtually any system with energy outputs and energy inputs, those are thermodynamic systems. Okay? Just about everything. A radio, a TV, a computer, right here in front of me. This Wacom tablet that I write on. These are systems with energy inputs, energy outputs. Okay? That's what thermodynamics is studying. Now, we're going to talk about 2 laws of thermodynamics. I'll mention the third one, Some people actually refer to a fourth one, but they don't call it the fourth law, they call it the zeroth law, because it really preceded the concept of the other three, but it came about later. So we won't dwell on that. What's the first law of thermodynamics? It's basically the conservation of energy, which we talked about in the last chapter. Okay? Energy is always constant. The total energy is. That it's neither created nor destroyed. That's the first law of thermodynamics. We usually refer to that in terms of three components. The internal energy of the object or material, or the system, the heat, and the work. Okay? Now let's think about it in a variety of ways here. The internal energy is basically largely potential energy. Okay? Heat is a transfer of energy, and work is that energy operating on the system. Okay? Now let's go back to, say, that air conditioning unit. When you compress the gas, you're increasing the internal energy of that gas. That produces heat. Okay? Now, if you take that heat and do something with it, like turn a compressor or turn a turbine or something like that, then you're doing work. Okay? Let's go to, I just found out this weekend that my wife's sister and her husband had bought a hybrid vehicle. Okay? And what that hybrid vehicle, one of the things it does, when you use the brakes on a hybrid vehicle, you are then taking the internal energy, well, actually it's more of an external energy of motion, the mechanical energy of the car, and rather than producing heat, you're producing electricity, because that is a regenerative, basically it's a generator that is using the kinetic energy of the car to produce electrical energy. Sure, there's some heat given off too. That's doing work on the generator to produce electrical energy. So you see, you have those components. That's not a great example, but you see them in there. Now it's stated in terms of changes of internal energy. So the change of internal energy is partly caused by adding heat to the system, or partly caused by doing work on the system or by the system. And all this depends on which sign is going which way. We'll talk about this. The application would be heat engines, your automobile engine, or other things like that. Okay? The internal energy that you get from, I don't know why that came out, from releasing the stored chemical energy in that fuel. Okay? If it's gasoline, diesel, whatever it is, that stored chemical energy that was in there from those ancient trees long time ago, storing that light energy from the sun into stored chemical energy in what later became petroleum. Okay? As you burn that, you produce heat, but that heat also does work on the system, which produces motion of the car. So there's an application of your heat energy, of the internal energy. Heat engine, sorry, I can't talk. Here is, I think I'm going to have to move this a little bit out of the way. Okay. Now, here's a simple heat engine. This is a piston, and this is not what your car does, but it sort of, in some ways, is like that. You put a weight on that piston, and that compresses the gas. So right now, the weight is doing work on the gas by compressing it. Okay? Now that's not part of your heat engine, not yet. If you added heat energy to that, the molecules now get more active and push that back up to the top where it was to begin with. Well, the amount of the change of the heat here, and the work you did to raise the weight from here to there, that is the increase in your internal energy that came about by heating the gas. Okay, the flame does work as the heated air expands and lifts the weight. Okay, so three things are happening. You're increasing the internal energy of the air by adding heat to it. You're heating that air, that's what enabled it to move up, and you're doing work on the system. Okay, now what formula could relate to that? Oh, they don't show it, do they? Well, maybe that'll come up. We'll see. So here's what we had. We had a high temperature region, okay, that's QH, and you had a low temperature region here, and your basic law of thermodynamics says that you always go from high temperature to low temperature, high potential to low potential. That's where it always goes. The heat engine takes some of that change of temperature and does work on the system. Not all of it produces work. Some of it goes to low temperature region that does absolutely no work. Okay, now you guys who have worked on cars, and those who haven't, you probably notice this as well. If you feel anywhere around that tailpipe, you feel a lot of low temperature region. In the piston, that's really, really hot. Okay, in the tailpipe, it's hot, but not as hot as it was there. In the piston, that's really, really hot, but in your radiator, you're blowing off low temperature region. So a lot of your energy that went into that internal combustion engine either got blown out of the tailpipe or got blown out of your radiator. You know, those vents and the fans, I can't think what you call them. Excuse me. Okay, sorry about that. The fins that are in there transfer the heat out of the water and it blows out into the air. So most of the energy that you burn in that in the pistons is lost to the tailpipe, lost to the air. Only a little bit produces the work of moving the car. Now, when you go to slow down the car, that's when you hit your brakes, and the brakes change more of that energy, kinetic energy of the car, into heat energy. Okay, so your heat engines are usually pretty low efficiency engines. We're getting much better at them, but they're still pretty low efficient engine. Okay, now, are they ever going to show us the formula? No, I guess not. So let me show you the formula. It's written in your text, and this is first law of thermodynamics, and they give it a strange title here. They call it the joule equivalent of heat. That's JQ, joule equivalent of heat, minus the work is equal to the change of your internal energy. U sub H, or they call it U2 minus U1. U2 minus U1. This thing is such a pain in the neck. Okay. Now, what this is your change of internal energy. This is delta U. That's what that stands for. U2 minus U1. UH, they were shown before, minus UL. That's what the high, low potential. This is the heat added, and that's changed to energy units, joule equivalent of heat times the heat, minus the work done. So the more heat you add, the hotter it is, but the more work you do by the system, the better your efficiency is, so you're getting more of it, but that's equal to your change of potential energy. Okay, internal energy, delta U. Okay, now in that same section, this is the top of page 107, you see another formula, and this is this one. The work done, now this has a caveat to it. This is if you have no change of internal energy. If this is constant, then you have W is equal to J, the joule equivalent of heat, times your Q high, and this is where the H and L comes from, minus QL. Now, I can almost guarantee you always have a change of internal energy. But if that's negligible or very small or zero, then this is the work that you do. The work is equal to that change of heat times the joule equivalent of heat, because work is measured in energy units. This is the joule equivalent of heat, so that's where that comes from. So there is your other definition. Okay? Now, I didn't mean to do that, but it did anyway. So I'm going to move this back down again. Okay. The second law of thermodynamics. First law, basically conservation of energy. The total change of internal energy is equal to the heat that you've applied minus the work that you did with that engine. That's what's happening. Second law of thermodynamics has three equivalent statements here. You may have more than this, but these are the three the book focuses on. One equivalent statement is no process can solely convert a quantity of heat to work, as in a heat engine. It doesn't happen. You can't convert all that heat into work. It does not happen. That second formula that we had there basically hardly ever happens. You can come close, but most of the time it won't happen. Okay? It says no process can convert a quantity of heat to work. Okay? Another way to say that is that heat never flows spontaneously from a cold object to a hot object. It just doesn't happen. You have to make it go that way. And they use refrigeration as the example. It doesn't automatically happen. You have to add energy to make that happen. Okay? The third way of stating this, natural processes always tend to a greater state of disorder. That state of disorder is called entropy. Okay? Now, I'm going to hold off some of my examples. No, I may not. I'll go on and give them to you now. Well, let's see. There's two reference scales. The first of these is the object's external energy. How much energy does the object have? This is the energy of global coherent motion. I throw a baseball to you, okay? I have done work on the baseball to make it increase its kinetic energy, to increase its speed so it gets to you. That's the total external energy of the baseball. An object's internal energy would be the energy of the microscopic, chaotic, incoherent motion of the material. That's associated with heat, mostly associated with friction. Okay? That's internal energy. This is energy we expect to get out of. This is moving your car forward. This is the loss of energy in the tailpipe, in the radiator, and in your brakes. It's just lost energy. Now, in a hybrid, you can convert some of that braking motion back into is somebody else trying to come in, or was that something I hit? I think we're still at 9 students. That's pretty low number. Okay. So this is associated with heat. Okay. The heat of your tailpipe, the heat of the radiator, the heat of your brake pads. Energy you cannot really use again. Okay. You might say, well then where can you use stuff? If any of you have ever used a hydraulic lift, okay, those are very, very efficient engines. You pump on it, or you have a compressor pumping on it, it raises that car up or whatever it is. That's a very efficient system. Internal combustion engine, not so much. Okay? Now, let's look at these three processes individually. Okay? The first statement, conservation of energy, heat engine. Now that sounds like what we said about the first law of thermodynamics. It is related. It says the input energy equals the output energy. Again, that sounds like first law. But not all of this energy is useful energy. Yes, total energy is conserved, but not all of it is useful. The efficiency of a heat engine, the work done per unit input energy, that's what efficiency of a heat engine is. The second law says the efficiency cannot ever equal 1. Yeah, the input energy equals output energy, but some of that output energy is wasted heat or wasted other kinds of energy, mostly heat. The second law says the efficiency can never equal 1. Some energy is always degraded down to a level you can't really use it. Remember that illustration they showed before, that low level energy at the bottom? Not usable. Now, if you think we drove up to Smith Lake over the weekend, okay, Karen's parents, my wife's parents needed to get out of the house. They had built the lake cabin there and stuff, and they wanted to go to the lake. So we are taking care of it now because they're in their middle 80s. So we went up there. I worked, burned brush, did a variety of things like that. Several of us worked, but we just had a good, pretty good time up there. Okay, but we drove by on Interstate 22, the new interstate that goes from Birmingham to Memphis. We drove by that, and passing by there, you see those great big stacks over there. Those great big old stacks over there were spewing out steam, I hope. I hope that wasn't dirty gases. I hope it was steam. Well, guess what? Some of the energy is always degraded. Yes, they were burning fossil fuels, probably. I think probably coal, to make electricity for us to use and all the things we use electricity for, but a lot of that steam was going up into the atmosphere. You cannot use it all. Some energy is always degraded. Okay, so it's not just internal combustion engines that are inefficient. Just about everything is, some to more degrees than others. So here's the formula we use here. The Q on the high side, the high energy, some of that produces work, some of it is wasted energy. Q on the low side. This is the energy output, the output energy here plus the work. Some of that is wasted energy. That's the work done per unit output. This is your input energy. There's your output energy. This is wasted. So the work divided by this, that is the efficiency. Always there's some lost. Okay, that efficiency is never equal to 1. QL is never 0. Okay, some energy is always degraded. Okay, and this is that formula. The energy is the work that you got out of the system divided by the energy you put in. Because this QL always has some positive value, it's not usable, so your efficiency is less than 1. Okay, 2 more equations for you. So here is the other way to look at the second law. Conservation of energy, this is now looking at a heat pump. The energy arriving in the high energy region is equal to the energy from the low energy region plus the work needed to move it to the high energy. So here, say you're compressing the gas, that you're doing work on the gas, compressing it, giving it more energy here, adding to the energy that it had down here. That's what a heat pump does. Work is required to move the energy from the cold region, low energy, to the high energy up here. That's the work that's doing. You're compressing the gas, increasing energy level from here to here. That's what a heat pump does. And basically a heat pump is a fairly efficient system. Not ever totally efficient, but it's fairly efficient. The energy arriving in the high energy region is equal to the energy from the low temperature region plus the work that you added to push it up there. Upgrading of energy by a heat pump is usually accompanied by greater degradation of energy elsewhere. That compressor that was doing that, it's getting hot, and that heat is not always captured here. Let's think about your refrigerator. Okay, that refrigerator is always removing heat from the air and doing its thing. If you were to go behind your refrigerator and fill up some of those tubes that are back there, they are producing enormous amounts of heat. So you're not being very efficient. Okay, there's always degradation. Always. Somewhere in the system there's degradation. So even though the heat pump itself is fairly efficient, something is being lost always. Okay. So here's the third statement. Real processes are irreversible processes. The measure of disorder is called entropy. Now, these are not exactly equivalent statements here. Okay. The second law in these terms, the total entropy of the universe is continually increasing, which is a very large statement. Okay, very large statement. But if you think about just our sun is sending out energy in all directions, we're capturing just a little narrow bit of it. Mercury's getting a lot of it, but what's Mercury doing with it? Absolutely nothing. Venus is capturing a lot of it, but not doing anything with it. We're capturing just a little bit of it, and we're not doing very well with that either. Okay, but hopefully we're doing better than we used to. Natural processes degrade coherent, useful energy. They always do. Okay, available energy of the universe is diminishing, so what's going to result in this? Eventually, they say the heat death of the universe. Well, how does that fit in with the Big Bang Theory? I have no clue. Okay, I can think of little pictures of it, but the big picture I can't even begin to grasp. Now, the direction of natural processes is always toward more disorder. Now, they will give this example: spilled milk will never unspill itself back into the glass. You can't make it happen. To get that milk off the countertop before it hits the floor, you have to do energy to get it unspilled. Okay, you have to, everything moves to disorder. The example I like a little bit better than that is, have you ever bought a deck of cards? Now, every deck of cards that I've ever bought, when I open them up, at one end you'll see the ace of spades followed by the king of spades followed by the queen of spades followed by the jack of spades, the ten of spades, the nine of spades, eight of spades, down through all the spades. Then you'll hit the hearts, the ace of hearts, the king of hearts, the queen of hearts, the jack of hearts, the ten of hearts, all the way down till you get to the diamonds, and then you get the ace of diamonds, the king of diamonds, all the way down till you get to the clubs, and then you get the ace of clubs, the queen, king. They're all facing the same direction, every card in order, right? Now, if you were to take those cards out of the box, okay, and put them, say, onto a sheet, okay, and then you and three friends get at each corner of that sheet and start tossing it into the air, and tossing it into the air, tossing it into the air, are you ever going to get that deck of cards to land back in the same order you got it? Never. Never, ever, ever in millions and billions of years will it ever happen. The more you do that, the more disorder you create. Okay? And everything moves to disorder. Now, the other example I think that your mom would probably like to use is your room. Does your room ever get more orderly the more you are in and out of it? I think not. I think things move toward disorder. The only way you ever get it in order is to add more energy to straighten things back up again, because it never fails. Everything moves to disorder unless you're adding energy to make it get back in. Okay? That spilled milk will never unspill itself back into the glass. All those are examples of the third statement of the second law of thermodynamics. Okay, that's the last slide in the slide set. Now, let me tell you right now what the third law of thermodynamics is. Okay, that's the one that says you can approach absolute zero, but you can never get there. Remember, absolute zero was that very coldest that you can ever be. The third law of thermodynamics said you can approach absolute zero, but you can never actually get there. Okay, we're not going to go into that any further. Now, there was a time that there was a big push to have the zeroth law of thermodynamics, and that was the law of thermometry, basically. That's saying that if one object is in thermal equilibrium with another object, then there is no energy transferred. But if this one has more energy than that one, then energy will flow from the high energy to the low energy. It's sort of like the first law, but this says it's basically the law of thermometry, that if you bring two objects together, they're going to come to an equilibrium. Okay, that's what a thermometer does. If you bring a thermometer against your head, then the thermometer is going to go from room temperature up to your temperature. That's what's happening. Okay, and that some people call the zeroth law of thermodynamics. Now let's talk about just a few other things here. One of these, there's a myths, mistakes, and misunderstandings. Some of these are pretty good, some of them are kind of dorky, but this is a pretty good one. Can you make your own fuel? Now that's your fuel, okay, not grow your own in it. Okay, never mind. Okay, basically, anything that you have to add energy to, you'll never get that much energy out of it. That's why using electrolysis to separate hydrogen from oxygen in water, and then burning the oxygen, the hydrogen to create a hydrogen fuel cell, you'll never get as much energy out of the system as you put into it to do it. It just doesn't work. Okay, that's just one example. You can read about others. Now, the person behind the science this time is a very interesting character, and here is Valerie. Glad she could make it today. Okay, we're finally broke double digits today with Valerie coming in, and that gives us 3, 7, 8, 9, 10. Yep, got 10 people. I don't know if we still have 10 people here, but let's see if we do. Nope, we're down to 9 again, but we've had a total of 10 at some point or another. Valerie, if you're in here now, we're right at the end of chapter 4. I was talking about the guy, the person behind the science. His name was Count Rumford. Sort of a beautiful looking guy, isn't he? He has a very interesting history. Okay, and I don't want to spend too much time on him. I don't know how much time I have. Oh, I forgot I had my clock here. Okay, we've got not quite 15 minutes, pretty close to it. Count Rumford was not really royalty. He was made a count. His name wasn't Rumford. His name was Benjamin Thompson. Now, we talked earlier about William Thomson, who was a compatriot of James Prescott Joule. Both of those were, oh, here comes Rodrigo. He must have been the one we lost. Now he's coming back. So he's here, but I already had him marked here. So we're now up to double digits again. We should have, yep, 10 students plus me. Okay, so don't confuse the two of them. They were both very bright people. William Thomson was Lord Kelvin, that they named the absolute temperature scale after, the Kelvin scale. Brilliant scientist, founder of thermodynamics, all that kind of stuff. Benjamin Thompson, with a P, William Thomson did not have a P in it. He was actually a colonist in America. Okay? Now, he, however, did not agree with the American Revolution. He thought we should stay British. So even though he was born in what is now Woburn, Massachusetts, and probably was, it was before we were a country. That was in 1753. He was very bright. He became a schoolmaster, a variety of things, moved around. He moved to Rumford, which is now called Concord. The first shots of the Revolution were fired in Concord, Massachusetts. Okay? No, I'm sorry, he was in New Hampshire. Rumford, New Hampshire, which later was renamed Concord, New Hampshire. Okay? And he must have been a pretty sharp guy. He married a wealthy widow, so that was interesting. But that's not what I'm getting at. What he did, because he opposed the revolution, he actually moved to Britain during the Revolutionary War. He was a brilliant engineer, more than maybe a scientist, but he was a good scientist as well. But because he was loyal to Britain, they made him a count. So that's how he became Count Rumford. Rumford, after the name of the town he had moved to in New Hampshire, even though he was born in Massachusetts, but they're pretty close. He went there. Now, why are we talking about him? Because, if you remember, back in Aristotle's day, he said there were 4 basic elements: heat, wind, water, and wait, I said it wrong. Earth, wind, water, and fire. Okay, 3 of those made a singing group: Earth, Wind, and Fire. They didn't have any water in them, but so people believed that was an element. That heat, fire, was an element. It had no mass, but they thought it was a component of nature. Well, the alchemists had gone crazy trying to take earth, wind, water, and fire, mixing them together and coming up with gold and platinum and silver and all these things. If those were the only 4 elements, you ought to be able to mix them together somehow to get these valuable materials out of them. And they were not successful, but they were very successful at developing a periodic table showing there were a lot more elements, and that even those elements were not elements. Okay, but Rumford, they still thought that heat or fire was some type of ethereal material. Okay, well, Rumford was doing work for the German government, I think it was. He was a really good engineer. He was boring out cannon for them. And how they did this at the time, they had the borer, they poured the iron casing, and then they bored out the core. Well, boring out the core was a really high intensive process. They had to have a pretty sharp bit. Poor old horse who went around and around in a circle. That's all he did, was go around and around in a circle, turning the bore, grinding out the interior of the cannon. Well, there was one cannon that was faulty. The material didn't pour right, and it was off. So they were going to throw that away. There was also a borer, the bit, that was really, really dull. And Rumford had already noticed this. The duller the bit got, the more heat was produced. Well, he was doing this somewhere probably near Munich, and he decided to show that heat was not an element. It was not something that was possessed in the metal or anywhere else. So what he did, Munich, Germany is fairly close to the German Alps. He sent up for the coldest water, maybe even icy, snowy water that he could find, took that dull bit, made that poor horse go around and around in circles, and in about an hour, with that dull bit and that defective cannon bore, he had that water boiling. Boiling! And there was that wasn't coming from the metal, it wasn't coming from the water, it wasn't coming from anywhere else, except it was changing the form of kinetic energy of the bore into heat energy of the water. So sure enough, he showed basically what Joule either showed in the future or in the past, that there was a Joule equivalent of heat. That heat was not a material thing, it was just another form of energy. So he was a pretty brilliant guy. Don't like his politics, but he was a pretty brilliant guy. Okay? So, with that, there is one last example in the text, and that is 4.8 on page 110, or 4.-24. Okay, so let's see if we can find a screen to write on. This one looks like it'll work. Okay, now a heat engine operates with 65 kilocalories of heat supplied. So this is our input heat, which we call the Q sub H. Q is heat in this chapter. Q sub H is equal to 65.0 kilocalories, thousands of calories. Okay? And exhaust, this will be the Q that's given off, QL. This is what goes out of the tailpipe there, is 40.0 kilocalories of heat. How much work did the engine do? Well, the difference between these, that formula we had earlier, was the difference between these is 25.0 kilocalories. And that would have, kilocalories, that would be the work done, because the QH is equal to QL plus W. If you remember that one. Let's see, is it right here? Yep, there it is right there. QH is W plus QL. So therefore W is equal to the difference between QH and QL. Okay? Now, but it asks for how much work did the engine do. This is in kilocalories. We don't usually measure work in kilocalories. We measure heat in kilocalories. So we need to get this to joules. Okay, so you have 25.0 kilocalories. Multiply that by a conversion factor to give you how many kilojoules. Now I like to stay in kilos if I'm there. So what do we do to make that conversion? We put the units in their place. We want the kilojoules on top, and we want kilocalories on the bottom, so you can divide out the kilocalories. Okay, and what was the joule equivalent of heat? If you go back a few pages, you'll see it on just about any page you reach to. I'm going to tell you where it is. Well, actually, it may be on the page real close to you, but let's go back. Page 104 or 4-18, and that's 1 kilocalorie. 1 kilocalorie is 4.184 joule. Now that's not how they express it. They express it as 1 kilocalorie is 4,184 joules. I make this a decimal place, and that's so much easier to work with. So what do we have? Pull out your calculator. How are we doing on time? Whoa, 2 minutes. Okay. Calculator tells us that 25 times 4.184 equal That's 104.6 kilojoules. 100, and they'll probably round that to 105 kilojoules. Now they probably, yeah, they leave it as that. They did it with 104,600 joules. Why? I don't know. If you kept it in kilojoules and kilocalorie, it come out that exactly. Okay, there's also a little concepts applied, thermodynamics in action. You can certainly read that. You'll probably find it pretty interesting. Okay, so let's sort of wrap up the chapter here because we're right at the end. Okay, as I say, after every chapter, nothing replaces reading the chapters. Okay, once you've read the chapter, hopefully you've already read it, probably read it again. When you do, there's a summary. Now this starts sort of small at the bottom of that page, but it goes for most of the first column of the next page. In fact, all of the first column, almost all of it. Okay. Then you have a summary of equations. Some of the chapters have quite a few. This one has 8, which is quite a few. Then the key terms. The key terms, not quite as many as some chapters have, but they're listed alphabetically, but they give the page numbers where they're first defined. So those would be good things to pay attention to. You'll see a lot of those key terms are italicized in your summary. Okay, then the most important thing to study, I think, is the concepts, applying the concepts, and there's 43 of these on pages 111, 112, and 113. They give the answers. They're all multiple choice. If you know these and can get these, you're going to do pretty well on the test, because the test is mostly multiple choice, not the same questions, but covering the same material. So the answers are given there. If you don't agree with the answer, bring it up in class and we'll deal with it. Then you have questions for thought. We have 17 of those. That's about normal. So quite a few questions for thought. Then you have applying the concepts. We have, or for further analysis, further analysis, 7. That's probably a few more than normal. There's 1 invitation to inquiry. You can certainly look at that. You may consider getting a paper topic out of that, perhaps. Hint, hint, don't forget your research paper. We're running out of November and only have 1 week in December. So please don't forget your paper topic. And then there's the parallel exercises. If you have the big book, the Group A answers are in the back of the book. The Group B are not. But if you have the little book, I think they left them out. I specifically requested they include the answers. I don't ever remember seeing that they did. Okay, where do we go from here? We skip chapter 5, wish we could do it, wave motions and sound. It's a great chapter, but I think for most of you, probably the following chapter will be a bit more practical for you. Maybe not as interesting, but practical. It's on electricity. So we're moving now to chapter 6, electricity. Okay, now I would love to take a break because I've been sitting here. Y'all can get up and move as much as you want to. I can't. Is it okay to take, say, a 5-minute break or less? Y'all all in favor? Okay, if anyone does come on and send some chats, tell them I'll be right back. I always fear taking a break that I might miss somebody, but I'm going to try to get back as soon as I can. I'm going to stop the recording for right now, and we'll room or in the class that today has been an absolutely crazy day. Last night I was kind of putting your lab together for today, but around 9 o'clock or so I was just running completely out of energy, so I didn't have time to type it. So I thought, well, I've got a half hour in the morning, and then I've got 2 hours between my third class and this class. Surely I can get it typed then. Well, 8 o'clock this morning, or shortly thereafter, I had started typing already, putting up your lab together. And I knew I wasn't going to finish it, but I had made decent progress. And about 8:15 or so was when I had planned, no, 8:25 or so was when I had planned to stop typing and hold the rest of it until my 2 hours between the third class and fourth class. So I was, it got to be about 8:23 or something around there when my phone rang. I went, uh-oh. It happened to be my boss. And they have decided, I think I was telling y'all this earlier, some of you weren't in here then, they are going to bring all the instructors back on campus, even though none of us are teaching on campus, but bring us back on campus so that we can register students next week, even though we can't register students. We're not allowed to. This new system banner, instructors can't register students. We can advise them, but we can't register them. So there I was, and we were going to have a meeting today at 12:30 where I had class that went till 12:45. I had 3 back-to-back classes from 8:30 until 12:45. So we're going to have a meeting then. So there went the next part of the time I was going to be typing on your lab. Well, then I also found out they had called a faculty meeting today. Well, just a staff meeting today, and it was required attendance. So there went the rest of my 2 hours, or most of the rest of the 2 hours that I had to type on the paper, your labs. So the lab is not typed up for you. Okay, sorry about that. Okay, but I think we can still do it. You're just going to have to write down your answers however you want to write them down. I just don't have a form for you to put them in. Now, if any of you can print out the form that we used 2 labs ago, I'm going to show you what I've done so far. And you can use the one that we used 2 labs ago. So what I'm going to do here is stop sharing this screen, okay, and exit that screen if I can. I can't. There, finally it did. And I'll discard that screen, put it away, and then what I'm going to do is open up that previous lab. Okay. First thing I think I'll do is minimize that.
Sorry, so is that lab 5?
Okay, lab 6, I believe it was. Yeah, let me see if I can get to it. I keep trying to shut things down and it doesn't go anywhere. Okay. Okay, yeah, I think you're right there. Okay, so let me, goodness gracious, it's all this mess here. Okay, I'll close that one out. And I don't know what this one is. I'll close it out. I'm trying to just get rid of some stuff here. And that shut another one. Oh yeah, these are probably left over from this morning. Yeah. Okay. I've got most of those out of the way now. So I'm going 2 places. It'll just take me a few minutes to get there. One reason I was a little late getting back, I went downstairs on the quick break that we had, and my wife drove up right at that time, and she had gone to the grocery store after she got off work. She needed help getting groceries in, so that's one reason I was a little late getting back here. Okay, now this is the lab. Tell me if this is the one you're thinking I was talking about. It's energy forms and changes. Was that the one that you had in mind? Lab 6.
Yes, sir.
Okay. If you will pull that up or print it out or something, we're not going to do what it says here, but we're going to do something very close to it. So I'm going to leave that open. Now the other one that I had, and this is the one I started working on, and it's really bothering me, I can't see it here. Okay, let me see if it's here maybe. Yeah, here it is. Okay, this one says lab 8. Okay, this is the one I started working on last night. Now I don't have it out there for you, but this is what we're going to be doing. Okay, so I'm going to leave that open. And then the next thing I'm going to do is here. Okay, I don't know why all these things are staying open. Okay, I'm trying to get this to open, and all it has is mail. So let me go to this one. There we go. Here. Okay. If y'all have the, I can't remember if I did one for this week. This is week 5, isn't it? I don't know if I have this up here, but this is the thing that we started with last time. And you didn't see this part of it because we went straight to the systems. We went to systems here. Remember her? We're not going to use her anymore, but she's already done all her work.
Okay, we can't see your screen.
Oh, you can't? Okay. All right. Sorry. See, when I move these things around, some things show up and some things don't. Okay. All right. Let's see what we've got here. Energy forms and changes. Okay. Remember her? Okay. We're going to do some of the stuff with her. Not with her necessarily, but we're going to do some with that. And this is where I'm going to have to move some things around again. Okay. And I'm also going to do, hopefully these will still be out there. This drives me nuts. Okay. I'll be right back with you. I've got to go back to this again. Okay. And I want to have this one. Okay. Now go back to, okay. All right. We're going to go back and forth between this and this. Okay. Why did that show up there? I don't know. We're going to minimize that. I don't think anyone else is waiting on the wings, are they? Was anyone trying to get in while I was gone on break? Did anyone could tell? Okay. So we're going to have this. Okay. All right. Now, here's where we're going to start today. And this is basically going to be the first part of the lab. Okay, and it starts just like the others. Go to Blackboard page for the course. Go to course content. Go to week 5, instructional materials. Scroll down to the lab simulation. So I think I got it on there. Click on simulations and then on physics. Scroll down to the energy forms and changes, which we just saw, and click on the triangle starting the thing. When it's downloaded, click on it, it will open, blah, 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 blah. Notice here it says click on intro. That's not what we did last time. So click on energy symbols and link heaters and place both the iron and the brick on each on a heater and attach the thermometer to each. Begin adding heat to the things. So that's what we're going to do, and these are the 2 questions we're going to answer. On which one does the temperature rise the fastest? Okay. That should be faster, but I'll, for some reason, there we go. And then we'll go on from there. So let's go back to energy forms and changes. Okay, we're going back to intro. Okay, this part we didn't do before. Okay, now I'm going to move this down here, this over here, and basically when you're starting over, go to this circle with the arrow going around in a circle, click on that, and it starts everything over again. Okay, can y'all see that? Okay, now I'm going to do what it said. We're going to move iron on one of these heaters. We're going to move the brick to the other heater. We're going to turn on the energy symbols and turn on the link to that these two heaters are going to heat at the same rate. We're going to take the thermometer, try to take the thermometer. It's not taking the thermometer. There we go. And put it on iron, and take another thermometer and put it on the brick. Okay. Now what I'm going to do here, and you saw the form there. So here's what I want you to do. Let's go back to the form. Okay. This one here. I'm going to begin adding heat to each. Okay. So what I want you on the form here is to say, even if you don't have this form printed off, the first thing is going to be iron and brick. And you're going to answer these two questions for the iron and the brick. Okay? So if you have just a blank piece of paper, write on it 1, iron and brick. Okay? That's all you have to put. Put your name. Be sure you put your name. Okay? Then do number 1, iron and brick. You can make that Roman numeral 1 if you want to, or whatever. Okay? And these are the two questions you're going to answer with the iron and the brick. Which one does the temperature rise the fastest or faster, and which one would have the higher specific heat? Now remember, when we started class today, I mentioned specific heat is the number of calories it takes to raise 1 gram of material 1 degree Celsius. So if the temperature is going up faster, that means it has a lower specific heat. If it's going up more slowly, that means it has a higher specific heat. Okay? So your first thing is going to be iron and brick, and you're going to answer which one does the temperature rise the faster and which one has the higher specific heat. So let's go back to our, any questions so far before I get started on it? Say that one more time. Cause what? I couldn't hear. Okay, okay. Okay, you may have come in after I started talking. Okay. I had so many interruptions today. This is my 6th Zoom session today. I had 4 classes of mine, this is being the 4th, one with my boss, one with the all the faculty. I had a phone conversation with my boss this morning, and this all is taking place in the half-hour office hours I had before my first class, and about 2 hours of office hours I had in between. That's when I had the meeting with my boss and the meeting with the faculty. So I had 0 time to make out the labs. Okay, so I was explaining to you, here's what we're going to be looking at. And so get you a clean sheet of paper, and on one of these, here's what you do. This is, if I had had a chance to finish the lab, this would have gone on. But see, I got 3 questions done. That's where I got interrupted this morning. Okay, and I haven't had a chance to get back to it. So if you want to start on a clean piece of paper and put number 1, iron versus brick. That's your number 1. You can do Roman numeral 1 or A or something like that. The first question you're going to ask is, on which one does the temperature of the rise faster, and on which one would have the higher specific heat between iron and brick. Now understand this, the higher the specific heat, that means the more energy it takes to raise 1 gram of the material 1 degree Celsius. So the higher specific heat would have the slower temperature rise because it takes more heat to increase the temperature. Got it? Sorta? So number one is iron versus brick. This right here. That's all you have to write down, and then write down this, on which one does the temperature rise the fastest and on which one has the higher specific heat. So I'm going to start the lab now, and it's going to be this one, energy forms and changes. I've got it all set up, and what I'm going to do is start raising the temperature. You'll see the flame come up. What you pay attention to is which one does the thermometer rise the fastest. Okay? Faster. Okay? So you tell me. And they're linked together. Which is the thermometer rising faster? The brick. Very good. Okay? Now, what does that indicate about specific heat of the brick? Would it be greater than that of the iron or less than that of iron? No, remember, it's sort of reversed. The higher specific heat means it takes more energy to raise the temperature 1 degree Celsius, 1 gram 1 degree Celsius. So it's always going to be flip-flop, right? If the brick rises faster, that means it has a lower specific heat. Now, if you got your books open, I don't know if you do or not, okay? If you got your books open, the specific heat was started on page 96, but the table for different material specific heat, you'll see that they don't have brick listed, but they do have concrete, which is similar to brick. That's 0.16, iron is 0.11. So brick, okay, I'm sorry, that does fly in the face of what we're trying to say. So well, brick isn't listed here, so you can't really get a clue here. But iron should have the higher specific heat because it takes more heat to raise the temperature of iron 1 degree than it did brick 1 degree. Okay? So iron should have the higher specific heat. Okay. And I'm trying to think if you realize that brick is sort of like a ceramic material, and it does take longer. It will heat up faster than the iron would. Okay, so that's the first part. Okay, I don't know how you want to say it, but let's move the brick off the thing and put water on the thing. Okay, so we got water up there. Let's take the thermometer off the brick and put it on the water. Okay, now you ready to start? So this will be number 2, iron versus water. Okay, same 2 questions. Which one does the temperature rise the fastest, and which one has the higher specific heat? So here we go, going to raise the flame. Which one? Say again? Iron rises the temperature the fastest. Which one would have the greater specific heat? Water. Now we can look at the table and it makes sense. Iron specific heat was 0.11, water 1.0. And you see how much faster the iron heated up than the water because its specific heat was much less. Does that make sense? Okay, so let's take the water off the heat and put the olive oil on the heat. Okay, and we're going to take the thermometer off the water and put it on the olive oil. Okay, now because we're not starting at the same temperature, we're going to reset. So you take your cursor over to the little circle with the arrow going around in a circle, click on it, and everything goes back. So let's put the iron back on. So this will be number 3, iron versus olive oil. Okay, now take a thermometer, put it on the iron, take a thermometer and put it on the olive oil. Okay, now we're going to turn on the energy symbols, and we're also going to link the heaters. Ready to go? So this is number 3, iron versus olive oil. See, the temperatures are starting at the same level. Let's increase the temperature. Which one goes up the fastest? Not quite. See, iron is passing it about the same, but you see iron is at the half point. It's nearing the next big one. It's lower down, but you see it's going to reach the top before the olive oil does, right? Okay, so iron would heat up the fastest, but it's like you said, it's very close to the same. Okay, unfortunately our table doesn't have any oil on it. Okay, so which you think has the greater specific heat? Should be the olive oil. You're absolutely right. Okay, so that was, say that again?
So number 3 answer is iron versus olive oil, or am I supposed to be adding stuff like
No.
iron is
Okay.
more so an olive oil? I don't know.
Uh,
I'm
okay. That's why I said I wanted that to be understood at the beginning. What you do for number 1, and that's why I said Roman numeral 1A, something like this, that's iron versus brick. That's the first part of this, iron versus brick. Okay? Which one does the temperature rise the fastest? That was the which? Do we need to go back and do it? Okay, the iron, the temperature rose the fastest. What does that tell you about specific heat? Which one would have the highest specific heat?
Mr. Fowler,
Yes,
I know you. I know you will not have a chance to retype this,
right.
but I can type up something really quick and send it out to the class after class is over.
Okay, if you want to, you can, but
Okay.
yeah. Um, so basically,
Iron rose the fastest.
okay, did it? I can't remember. Which rose the fastest, iron or brick?
Iron.
Iron it did, okay. So that meant that the brick had the higher specific heat, right?
I'm sorry. Are we on number 1 or number 5 or 3?
Okay,
1. We're on 1.
okay,
Right, B. I'm sorry. So number 1 would be brick.
okay, that's what I thought.
Temperature rose the fastest.
In brick, that's what I was thinking. That was brick. So number 2, for the first setup, which was iron versus brick, the temperature rose faster with the brick, right?
Yes.
Okay, which meant the iron had the higher specific heat, right?
Right.
Okay, so that's your first setup, however you want to call that, iron versus brick. Okay, then the second setup was iron versus water. Okay, and you answer the same 2 questions. Now you could make them 3 and 4 or whatever. See, that's what I was going to do next, was the place iron and water on the heater, and there I got that far. Okay, and the phone rang right as I was right here. Okay, and that's as far as I got. So the next one was reset the system, click on the energy symbols in the link because they turn them off every time you reset. Place the iron on one heater and the water on the other, and attach a thermometer to each. Begin adding heat. On which one does the temperature rise the faster? Between iron and water. Iron rose the faster, okay? Water had the higher specific heat. So that's the second comparison we did, okay? Okay, now go to the next one, and the next one was iron versus olive oil. And which one did it rise the fastest? Okay, so which had the olive oil had the higher specific heat? We didn't have anything to compare it to, but that's it. Now you'll notice also, well, we'll forget about that now. We let the iron get quite a bit hotter, so it hasn't cooled off. Okay, our number, that was number 3, right? The third comparison. So we're going to reset everything. So we've done iron versus brick, iron versus water, and iron versus olive oil. So now we're going to do brick versus water. Okay, and we'll put the energy symbols in the place. We'll link the heaters. We'll put a thermometer on each. Oops, try to put a thermometer on each. Okay, now I'm going to add the heat. Now this one is brick versus water. Okay, I'm going to add the heat, and you tell me which one does the temperature rise the faster. Brick. Which one has the higher specific heat? Water. Very good. Any questions on that? So that was the fourth comparison, right? We had iron versus brick, iron versus water, iron versus olive oil. Now we've had brick versus water. Okay? Now I'm going to reset. Y'all okay with this? And we're going to put brick on one and olive oil on one. I need to keep from breaking the beakers there. Okay. Now, going to put a thermometer on each and initiate my symbols and link the heaters. Okay. So here we go now. Increase the heat. And which one rises faster? Okay, the brick is rising faster. You're absolutely right. So which one has the higher specific heat? Olive oil. Excellent. Okay. Is everybody following this now? Okay. So let's reset. And this time we're going to put water on one and olive oil on the other one. Okay, this is our, which one is this? 1, 2, 3, 4, 5, 6. This is our sixth comparison, right? Going to put a thermometer on each. Put our symbols in place and link the heaters so they both are heating at the same rate. Okay, ready? All right, start adding heat. Which one does the temperature go up the faster? Olive oil. Which one has the higher specific heat? Absolutely. Water has one of the highest specific heats of anything. Okay, so that gives us 12 answers right there, right? This is our sixth comparison, 12 answers. We've got at least 13 more to go. Okay, are there any questions before we leave this one? Okay, none whatsoever. Okay, now we're going to go down here to systems. Okay, we remember her, don't we? Okay, now this is where I suggest that you go back to yeah, lab 6, exactly. And this is how lab 6 looks. And this one we had the that was the blue pull on the faucet, and then we did the paddle wheel. Okay, after we did the blue pull on the faucet and the paddle wheel, we went to the beaker, changed the beaker of the water into an incandescent light bulb, and we did number 2. Sorry. Then we changed the faucet to the bicycle with the gal on the bicycle, and then we did that one. And then we did, okay, that pretty much took us to the end. So what we're going to do now is, and you can use a form similar to this one. It won't quite be the same, but we're going to be similar to it. And let's go back to energy forms. Okay, we've already done the beaker, the bicycle with the water, right? That was one we did before, right? Okay, we've done the faucet with the water. We didn't do the sunlight. So let's this time do the sunlight, and it doesn't make any sense to have it hit the paddle wheel, so we're going to have it hit a solar cell. Okay, now a lot of our questions are going to be the same as what we had here. So let's go back to our questions here and see what they are. Okay, nope, I hit the wrong one. I thought I had that one there. Go back to, and some of these may be on the form too, but that's it, lab 6. Okay, now I got to move y'all a little bit because I can't advance. There we go. Okay. All right. This one will start a lot like it is here. Go to the Blackboard page, blah, 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 blah. Okay. Go to energy symbols, blah, blah, blah. When you see mechanical, think either gravitational potential energy or kinetic. Most of what we're going to do on the one we got set up has neither one of those. So don't worry about those. So I'm not going to do a blue pull. Okay. We're not dealing with mechanical energy. We're not doing with gravitational potential energy. Okay. What we're doing with is have the sun fall on the solar cell. Okay. Now, that's what our first one's going to be. Sun on solar cell. Okay. Now, the first question is, what form of energy is coming from the sun? Okay. So that's the first question. What form of energy, not mechanical energy, what form of energy is coming from the sun? The second one, in what form does it change when it hits the solar cell? Okay. Now, what form does the solar cell give it? Okay. Now, some of these we may not have anything on. Okay. Is all the energy of the sun converted to the energy of the solar cell? That's an important question. Is all the energy of the sun converted to the energy of the solar cell? The solar cell, this isn't the paddle wheel anymore, the solar cell is connected to an electrical generator. That's what a solar cell is. What form of energy does it change? To what form of energy does it change? Okay, as that energy goes through the heating coil, because we've still got the water there, in what form of energy does it change? And as more of the energy enters the water, what does the thermometer do? Okay, let's see if there's one more question. Um, and what we'll do then, rather than turning the faucet off, we're going to add more clouds. Okay, so this next question will say, after clouds are added, less energy is coming in. What happens to the units in the water, and what does the thermometer do? Okay, now we'll try to do those. So our number one here is it's going to be the sun and the solar cell. Okay, and then we'll try to answer as many of these questions as possible. So the first thing that you do next is sun versus solar cell. Okay, so let's go to the lab. Sorry I didn't get these done. So there's the sun, there's the solar cell. Why is that? Oh, it's already been cooking. So let's start over. Okay, it goes back to the gal. Okay, so let's take the sun here, the solar cell here. Now it starts immediately. Let's show the energy symbols and let's go to town. What are the energies coming off of the sun? What are the light energy? When it hits the solar cell, what energy does it become? Electrical. Do all of the light energy forms from the sun change to electrical? No, some of them no. Very good. Exactly, as light. Okay. What happens when they hit the heating coil? When the electrical units hit the heating coil, what do they become? Thermal, exactly. What happens to the water temperature? It rises. Okay, you got the general idea? Okay. Now let's go from no clouds to lots of clouds. Okay. What happens? What do you notice about the energy? Yes, exactly. So therefore there's no light energy or very little finding its way to the solar cell. So none of it gets transferred into electrical. None of the electrical changes into thermal. And what happens to the thermometer? Well, yeah, right now it doesn't look like it's changing, but you see some does leave, and when it does, it goes down just a little bit. Okay? Very, very slowly. Okay? Now, those were a lot of questions really fast. Did everyone get them all, or do I need to go back over some of them? I'm sorry I didn't get this typed up, but I didn't think you wanted to do 2 more hours of class today. Yeah, go ahead. Okay. Okay. Let's, okay. Let's take the clouds from lots to none. Okay. First question, what kind of energy units are coming off the sun? Light energy. Excellent. When the light energy hits the solar cell, what does some of those become? Electrical. Do they all become electrical? No, a few of them do reflect back as light. When the electrical units go through the heating coil, what do they do? Not electrical, they were thermal, exactly. And what happens to the thermometer? Yeah, the temperature rises. Okay, exactly. The thermal is sort of heat. Okay, so then what happens when it goes from no clouds to lots of clouds. What do you notice happening? Sounds good. Okay. While at the same time, you start the hot water over here continues occasionally to lose thermal as it goes up into the atmosphere. And what happens to the temperature? Slowly goes down. Absolutely. All right. How many more questions was that?
I have no clue, but there's gonna be a paragraph.
Okay, that would be fine. But try to make sure that I can understand that you got that. Have a blank for every question. Okay, that we can do.
Light. Number two was electrical.
All right.
Number three was low. Number four was thermal. Number five was it rises.
Okay.
Number six was no light energy transfers. And number seven was the thermometer goes down.
Okay, that sounds great. All right. So we had 12 and 7. We're up to 19. Okay. So this time I'm going to reset. Okay. And this time we're going to use the teapot. Okay. Now the teapot we assume has water in it or something like that. What we have is a paddle wheel here like we saw with the faucet earlier, if you remember that one 2 labs ago. And then the paddle wheel is going to turn a generator, and that's going to do something to the water. Okay, so what I'm going to do here is, oh, need my energy symbols. Okay, there they are. All right, so this is teapot, paddle wheel, water. Okay, now I'm going to increase the energy of the teapot and tell me what energy forms you see changing. What's coming out of there? No? Ther Thermal, exactly. Now what comes out of the teapot though in steam is, you're right, mechanical. Now which form of mechanical? Remember, it's either kinetic or potential. Kinetic, you're absolutely right. So you got thermal coming out of the flame, heating the water, increasing the kinetic energy of the steam. That turns the paddle wheel, which again is what kind? Kinetic. And when the paddle wheel turns the generator, what kind do you get? Electrical. Excellent. When the electrical hits the heating coil, goes back to being thermal. What happens to the water temperature? It rises. Excellent. Okay. Does anyone need those to be gone over again? Okay. All right. Do you want to restart it all? Okay. Okay. So we have to bring our teapot back. And I think we're ready to go then. Oh, we need our energy symbols. Okay. Here the teapot's cold, everything's cold. As we increase the flame here, what kind of energy comes out of the pot, out of this? Thermal. Okay. The thermal heats up the water, making steam. That steam has what kind of energy? Mechanical. And there's a few thermals that come out too, but it's mostly mechanical. That turns the paddle wheel, which is what kind of energy? Kinetic. Yeah, both of them are mechanical and both of them are kinetic. And when it turns the generator, what kind of energy does it become? electrical. When the electrical energy enters the heating coil, that becomes thermal again. And what happens to the temperature of the water? It rises. Very good. Okay. Now, when I guess we had this question at the end of the other one, when I take the heat off the pot, what do you notice happens? No thermal energy coming out of the pot, out of the bucket. No more, not much more steam is turning, it's going down, and so less kinetic energy, both of the steam and of the paddle wheel. So gradually fall. You're absolutely right. Very good. How many more questions did that give us? Nine more. So we were 12 plus 7 was 20, no, it was 19 plus 9 is 28. That gives us our 25. Do you want to do a few more or stop it there? Okay, I thought maybe you would say that. We could have put our incandescent light bulb in and done the same thing with either of the solar or the teapot. We did it with the others before. Or we could have put the uh, compact fluorescent in, done the same thing with this, or we could have done the propeller and done the same thing there. Did you want to see what happens with any one of those? Let me know. I'll be glad to show them to you if you want me to. Okay. Okay. You want to start with the incandescent light bulb. Okay. Do you want to use the sun and the solar shield, or do you want to use the teapot and the paddle wheel? Okay, so we'll do sun here and we'll do solar shield there because there's nothing it can do to the paddle wheel. So it's going to start pretty quickly, so let's see what happens. Okay, there's the solar shield and the same thing we had before. The light energy from the sun hits the solar shield. Most of it becomes electrical. However, some of it does reflect off as light. The electrical lights up the bulb, and when it does, you see some come off as heat. Quite a bit comes off as heat, but some of it comes off as light as well. Okay? But with the incandescent bulb, quite a bit of it is heat. You see all this heat in here? Some of it changes the light, but it all starts as heat. Some of it escapes as heat. That's why incandescent light bulbs get so stinking hot. Okay? That's where most of your energy loss is with an incandescent light bulb. Okay? Now, let's go to the compact fluorescent. Okay? Everything else is the same here, but now the electrical becomes mostly light. Every now and then you see a heat go off, but most of it is light. Compact fluorescents typically are not nearly as energy wasteful as incandescent. Now this was an older lab. It doesn't have LED lights. That's even more light, less heat. Those are LEDs. That's what I've got in the one up here now. Okay? Make sense? Okay. You want to go to the propeller. Okay, propeller. The electrical energy here transfers into what kind of energy here? Say again? Okay, that's fine. I'm glad he's interested in science. What kind of energy does the propeller produce? Mechanical. And which form of mechanical? Kinetic. You're absolutely right. Okay, very good. So all the rest of it is pretty much the same. And by the way here, based on what we did today, you'll notice this has very little heat loss. There's a little bit going up. So usually these systems are far more energy efficient than ones that have a lot of heat. Whenever heat's involved, you have a lot of wastage going out to the atmosphere. And that's when your efficiency goes down, based on what we did today in class. Does that make sense? Okay. Now, one disadvantage of this system, notice there's no heat loss here either. Okay, it's all either reflected back into the atmosphere as light or it becomes electrical. And there's very little heat lost here. Okay, every now and then you'll see one go up, but most of it becomes mechanical. And that's true about a lot of your electric motors. They don't tend to get as hot as other motors do. Okay, they can. There went one red that went up. Okay, do you want to look at any others? But this is the disadvantage of solar. On a cloudy day, less gets to your solar panel. A little bit does, but not a lot. On a very cloudy day, almost none do. Okay, so that's what's happening there. Now what they didn't show here is any wind energy. Wish they had, but that was really tough to do. With a very cloudy day, nothing's hitting the solar cells, so therefore you have no electrical convergence here, and the propeller stops. No mechanical energy. That's the disadvantage of solar on very cloudy days, and today was one of those days. You would have had very low potential for solar energy today. It was a little rainy most of the day, so it was very, very cloudy. I think we got a budding scientist, don't we? That's wonderful to hear. Wonderful to hear. Makes these old ears feel happy. All right. Anything else? We could go back to the teapot and the light bulbs and the paddle wheel, but not much is going to change. But I'll be glad to do any part of it over again. Anything you want to do. Does everybody sort of understand what you need to turn in now? That first part, the intro part, you compare each of those devices. Iron versus brick, which one does the temperature rise the fastest? What does that tell you about specific heat? Okay, then iron versus water. Which one does the temperature rise the fastest? What does that tell you about specific heat? Iron versus olive oil. What does that tell you? Which one rises faster? What does that tell you about the specific heats? Then brick versus water. Which one does the temperature rise faster? What does that tell you about specific heat? Brick versus olive oil. Which does the temperature rise faster? What does that tell you about specific heat? And then water versus olive oil, the one we ended with. What does that tell you? Which one rises faster? And what does that tell you about specific heat? So that's our first 12 questions. That's almost half the lab right there. Okay. The systems, I can't remember which order. I think we probably did the sun and the solar cell and the water, I think is what we did first, right? And then we looked at all the energy changes that went on then. Okay. Then I think after that we did the teapot in the water, didn't we?
Yes, with the water paddle.
Oh, with the water paddle. Okay.
No, no, no.
Oh yeah, because it wouldn't make any sense with the solar cell. Yeah. And then we heated up the added heat to this and made steam, and we talked about what happened there. Okay. And then did that just about do us in? I think it did, didn't it? Because we had 7 and 9. That made 16 plus 12 was 28 or something like that. Maybe a few more, something like that. And then we looked at a few others. Any questions? Do you think this lab was helpful? Okay. Can I help with any of the confusion? Okay. Um, sometimes we'll talk too fast, so y'all need to slow me down if I'm ever talking too fast.
Yeah, I think too, with us not having questions specifically for
I
you,
know I'm so
a little bit confusing.
yeah. You would rather had class for the next 2 hours, wouldn't you? You didn't want the lab with no questions, did you?
Of course, we would have rather had you lecture.
I think your nose is growing, isn't it, Pinocchio? What you say?
That's my son. I'm sorry.
Oh, okay, that's fine. That's happy. Okay. All right. Anything I can do to help clear up something, I'll be glad to go over any of it again. We got almost a whole hour we can play with.
No, but now I got to go over this whole lab with my child now.
Oh, I see. Are you able to run it on your computer and go over things like that?
Yes, I can.
Oh, excellent, excellent. Sometimes these don't work well on, student computers. I don't know if they don't have the right JavaScript or something like that on it. So I'm
I
glad you
have to
can do
use
it.
JavaScript for my job, so
Okay,
that's the only reason why I'm able to.
right. Good deal. Okay, the next lab will be based on electricity. I don't know which one it'll be. It'll either be Ohm's law or one of the others, but we'll do that one. Oh, and did I go over before what the end of the term is going to be like?
No.
Okay, we have class today and Thursday. Thursday we'll start chapter 6, that's electricity and magnetism. And then we'll have a lab on, I believe it'll probably be Ohm's law. Okay? That one I think I've already got prepared. I may have to make a few minor changes, but I think it's pretty much in place. Okay? Then next week, oh, and do y'all know that there's no class tomorrow? Any kind of class tomorrow. Tomorrow is Veterans Day. The school is closed. There are no classes, any kind of classes tomorrow. But that doesn't bother us for Thursday. We'll be back here on Thursday. Okay. Now, next week, we have class Tuesday and Thursday. Most of that time will be in chapter 6. Chapter 6 is a fairly long chapter. We'll be in that. So we'll have labs Thursday in chapter 6 and Tuesday and Thursday of next week in chapter 6. Now I'm just guessing now, okay? Then on the week after that is Thanksgiving week. And if I'm not mistaken, Thanksgiving, the students, you don't have anything during Thanksgiving week. Is that your understanding?
That's my understanding.
Okay, so we have meetings Monday, Tuesday, and Wednesday, but there's no classes Monday, Tuesday, and Wednesday. Then Thursday and Friday, the college is closed. Don't try to get in touch with anyone. Nobody will be there. Okay, so that gets us through Thanksgiving. Then the week after Thanksgiving, we have one more week of class. That's Tuesday and Thursday. We have that week of class. And if you're in a full-term class, that's it for classes. But in this class, because we're mini-term, we also have class the Tuesday of the following week. And after we do that class on Tuesday of the following week, then I'll give you your final exam, and you do it and turn it in by Thursday. And that final will be probably one of the easiest tests you've had all term, because it'll be matching, because you only have that 2 days to turn it in. I didn't want to give you anything too hard, so that's going to be hopefully pretty good. It'll cover all 6 chapters we did. But
Okay, never mind. You answered my question I was about to ask.
okay, yeah, the final exam will be comprehensive. We will have, oh, remind me of this. Since we finished chapter 4 today, we just had our last lab on chapter 4 today, I will post the chapter 4 test this evening sometime. Okay? If I don't get it done this evening, it may be tomorrow, but I'll try to get it done this evening. Okay? You can do that anytime. Remember, there's no classes tomorrow, so you can work on it then if you want to, or whenever. Okay, so the last chapter we do is chapter 8, which is a chemistry chapter. It only has one lab for it that I know of. I don't know if I'll be able to find another lab for it, but we'll try to do what I can. I did notice there are a few things in chemistry out there in the simulations, but I don't know if it's anything we'll cover in that chapter that we'll be able to do. If I find something, we may be able to have some more labs. Okay, but it may be toward the end of the chapter, end of the term, we'll have fewer labs, because one thing, I don't want to have you a lab every day and then you got all these labs that you have to do at the same time you're doing the last chapter test, and same time you're trying to do your final exam. That just piles it on too high and too deep. So we'll probably only do one lab for chapter 8. Now if I find one really easy one, we may do another one, but the one I've got made out now is pretty straightforward, I think. All right, and that will end the term. I mean, we're in week, what is this, week 5 now? Yeah, so we only have Thursday, Tuesday and Thursday of next week, skip a week for Thanksgiving, Tuesday and Thursday of the following week, and then Tuesday, and then the final exam on Thursday of the last week. So that's all, folks.
Mr. Powers.
Yes.
So after that, we're out until after the first of the year.
Yeah. Uh, the okay.
I'm sorry.
Okay. The
Okay, I'm sorry. You got my attention now.
okay. The there are 2 weeks in December. Okay. There's this week, next week, and then Thanksgiving week. That finishes November. Then you have 1 week in December of class, another week that for full-term students, that's all final exams. For mini-term 2 students, it's 1 day of class and 1 day of final. I'll give you the final the last day of class, that Tuesday, and get it into me by Thursday or Friday if you can't need it. Okay.
So, with regards to our research paper, if we turn it in during the week of Thanksgiving,
Yeah. Anytime in the
is
week
that
of
a point?
yeah, anytime in the week of November, anytime in the month of November, you get that point. If you turn it in December, you just get your score. Okay. If you turn it in after that last day of class, which is the Tuesday of, you know, the second week in November, if you turn it in Wednesday, Thursday, or Friday after that, you start losing points. So don't go there. But if you can get it to me in the month of November, you get your bonus point. Glad you asked that. Okay, so basically we're going to have at least 3 labs in electricity. We got 1 test coming up for chapter 4, the labs you just did today. 1 test for chapter 4. At least 3 labs for electricity. There may be 4 of them. Then a test in electricity. That's chapter 6. And then we have at least 1 lab for chapter 8 and a test for chapter 8, and then the final exam. So there's still a bit yet to go, but you got most of it behind you right now. All right, glad to. Any other questions? Does anyone want to see any of this again? All right, if I hear none, I'm going to take off the energy forms and changes, and I'm going to stop sharing with you. Okay, and I'm going to end the session. Do any of you have any questions before I end it? Yeah, this will be lab 8. If you'll put lab 8, be sure you put your name and have me, I can't remember now, 28, 29 blanks, okay, that you filled in correctly, of course, okay. That will be today's lab. And you can use either of those other two forms, just change the words on them if you want to. That would be fine too. Or if you want to just put them on a blank sheet of paper, that's fine too. All right. Any questions? Okay, you ready for me to end it? Okay. I want you to have a very fun, good, but very safe Veterans Day tomorrow. Okay. And then we'll see you on Thursday. Okay. All right. Bye bye.